Something 10 times heavier than Earth is hiding in our solar system, and we have no idea what it is. 50 billion miles from where you sit right now, an object is warping the fabric of space itself. We know it's there because we can see its fingerprints. 6 frozen worlds drifting in the outer darkness, their orbits bent into impossible alignment, pulled by a force that should not exist. The math is undeniable. The gravitational signature is clear, and yet when we point our most powerful telescopes at the exact coordinates where this thing should be, we see nothing. For nearly a decade, astronomers have been hunting what they call Planet 9, a hidden giant lurking at the edge of the solar system, massive enough to reshape the orbits of everything around it, dark enough to vanish against the void. Observatories around the world have scoured the sky. Supercomputers have run millions of simulations, and in 2023, a Japanese infrared telescope detected something, a faint thermal signature radiating from the exact patch of sky where Planet 9 is supposed to exist. But here is where the story turns, because the more scientists study the gravitational data, the stranger it becomes. A planet that size, that far out, moving that slowly, it fits. But so does something else, something smaller, something far more terrifying. A primordial black hole, roughly the size of a grapefruit, 10 Earth masses compressed into an object you could hold in your hand. And in 2025, the Vera the 100th Rubin Observatory will begin the most comprehensive sky survey ever attempted. Within months, we will have our answer. Either we find a 9th planet hiding in the dark, or we confirm that a black hole has been silently orbiting our sun since the solar system was born. Either way, nothing will be the same. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. The solar system has a boundary problem. Beyond Neptune's orbit, out where sunlight arrives so faint that noon looks like twilight and a year lasts longer than most human civilizations, something is pulling, not a gentle tug. A systematic, organized gravitational force, strong enough to wrench entire worlds into orbits that make no sense. Objects the size of small countries are being herded like sheep by a shepherd no one has ever seen. And for the last decade, every time astronomers have tried to explain what's happening out there without invoking a hidden planet, the math has politely refused to cooperate. This is not the first time humanity has played this game. We have found planets by their shadows before, twice actually. Both times, the story started the same way. Astronomers staring at data that wouldn't behave, orbits that refused to close, and a slowly growing suspicion that something massive and invisible was hiding just outside the edge of the map. In 1781, William Herschel pointed his telescope at what he thought was a comet and accidentally discovered Uranus. It was the first planet found in recorded history that hadn't been visible to the naked eye since the dawn of civilization. For a while, that discovery felt like the end of the story. The solar system had 7 planets. The outer frontier had been reached. Then Uranus started misbehaving. Its orbit didn't match the predictions. It was drifting, pulled by something that shouldn't be there. By the 1840s, mathematicians in France and England had independently calculated where the unseen object had to be based purely on how much Uranus was being tugged off course. They pointed their telescopes at that patch of sky, and there it was, Neptune, a planet found not by seeing it, but by reading the distortions it carved into the motion of its neighbor. The discovery was hailed as one of the great triumphs of mathematical astronomy, proof that Newton's laws worked so perfectly you could use them to find entire worlds sight unseen. Then the process repeated. Neptune's orbit also showed anomalies. Subtle ones, but enough to convince astronomers that there had to be a ninth planet even farther out. The search lasted decades. In 1930, a young astronomer named Clyde Tombaugh, working at Lowell Observatory in Arizona, finally found it, a faint dot moving against the stars. They named it Pluto and declared the solar system complete. 9 planets, orderly and accounted for. Except Pluto was tiny, far too small to have caused the orbital perturbations that led to its discovery in the first place. As measurements improved, it became clear that Pluto's mass was nowhere near large enough to pull Neptune around. The anomalies that had justified the search turned out to be measurement errors. Better data erased them entirely. Pluto, it seemed, had been found by accident, a cosmic fluke. And by 2006, after the discovery of other similar objects in the outer solar system, Pluto was reclassified. Not a planet, a dwarf planet. One member of a whole new population of icy bodies drifting in the frozen fringe beyond Neptune's orbit. That population has a name, the Kuiper Belt, a vast ring of ancient debris left over from the formation of the solar system, stretching from about 30 astronomical units out to 50 or more. 1 astronomical unit is the distance from Earth to the Sun, roughly 93 million miles. Neptune orbits at 30. Everything beyond that is Kuiper Belt territory, cold, dark, and full of objects that have been sitting in deep freeze for 4.5 billion years. Most of them are small, rubble, cosmic snowballs a few dozen kilometers across. Some are bigger. Pluto is one of the big ones, so is Eris, Makemake, Haumea. These are the trans-Neptunian objects, or TNOs, and for a while they seemed unremarkable. Frozen relics, interesting to planetary scientists, sure, but not the kind of thing that would upend our understanding of the solar system's architecture. Then astronomers started finding the weird ones. In 2003, a team led by Mike Brown at Caltech discovered an object called Sedna. It was big, about 2/3 the diameter of Pluto, and its orbit was completely wrong. Sedna never comes closer to the Sun than 76 astronomical units. For context, Neptune is at 30. Pluto's orbit at its farthest reaches 49. Sedna doesn't even get that close. At its most distant point, it swings out to nearly 1,000 astronomical units. A single orbit takes more than 11,000 years. And here's the part that made no sense. Sedna is too far out to have been scattered by Neptune. The giant planets, Jupiter, Saturn, Uranus, Neptune, spent the early solar system flinging smaller objects around like cosmic pinballs. That's how most distant orbits are explained. A close encounter with a giant planet billions of years ago kicks a smaller body onto an elongated path, and it stays there. But Sedna never gets close enough to Neptune for that explanation to work. Something else put it out there, something that isn't supposed to exist. For a while, Sedna was treated as an outlier, one strange object in a big solar system. Weird things happen. Then in 2012, Scott Shepard at the Carnegie Institution for Science and Chad Trujillo at Gemini Observatory found another one. They called it 2012 VP113, and its orbit looked disturbingly similar to Sedna's. Same kind of extreme detachment from Neptune, same ridiculous distance at closest approach, more than 80 astronomical units, same long, lonely trip into the outer dark. 2 objects with nearly identical orbital characteristics sitting in a region where they shouldn't exist and where nothing should have been able to put them. Shepard and Trujillo published their findings in 2014 and included a line that would turn out to be prophetic. They noted that the orbits of these distant objects seemed to share a common orientation, Not just similar shapes, but similar alignments, as if something had organized them. They suggested, cautiously, that a large, unseen planet might be responsible. The paper didn't get much attention outside specialist circles. It was a hypothesis, not a claim. Interesting, but not urgent. The solar system had spent the last 70 years teaching astronomers to be skeptical of unseen planets. 2 years later, the hypothesis became a bombshell. In January 2016, Konstantin Batygin and Mike Brown, both at Caltech, published a paper in the Astronomical Journal with a title that didn't waste time being subtle: Evidence for a Distant Giant Planet in the Solar System. They had taken the clustering idea that Shepard and Trujillo hinted at and run it through a full dynamical simulation. They analyzed the orbits of 6 trans-Neptunian objects, Sedna and 2012 VP-113 among them, all of which shared extreme orbits with perihelia, closest approaches to the Sun, beyond 30 astronomical units and semi-major axes greater than 150, and all 6 orbits pointed in roughly the same direction. Their perihelia, the points where they come closest to the Sun, were clustered within a narrow range of angles, and their orbital planes were tilted in a similar way. Batygin and Brown calculated the odds of that clustering happening by chance. The number they arrived at was small, very small, 0.007%, less than 1 in 1,000. In other words, if these objects were scattered randomly by known processes, you would expect to see this kind of alignment once in about 140 solar system simulations. The paper didn't just point out the problem, it offered a solution: a single planet, massive and distant, orbiting the Sun on an elongated path tilted relative to the plane of the inner solar system. Batygin and Brown estimated the planet's mass at roughly 5 to 10 times that of Earth. They placed its orbit somewhere between 200 and 1200 astronomical units from the Sun, with the most likely semi-major axis around 400 to 700. The orbital period, how long it takes to complete one trip around the Sun, came out to between 10,000 and 20,000 years. And the orbit itself was highly elliptical, meaning the planet spends most of its time in the deep outer system, far beyond the range of even our best telescopes. They called it Planet 9, not Planet X. That name had been used before for the hypothetical planet that was supposed to explain Neptune's orbit and led to Pluto's accidental discovery. Planet 9 was deliberate, a reboot. This wasn't speculation based on vague perturbations. This was a specific prediction, grounded in orbital mechanics and backed by simulations showing that a planet of that size in that location would naturally produce the clustering they were seeing. The announcement made headlines, not just in astronomy journals. Mainstream news picked it up. The possibility that our solar system, a place we assumed we had fully inventoried, might contain an entire planet we had somehow missed, was the kind of story that didn't need embellishment. Caltech issued a press release. Batygin and Brown gave interviews, and they were careful. They emphasized repeatedly that they had not seen Planet 9. They had found evidence for it, gravitational evidence, the same kind of evidence that led to Neptune. They even acknowledged that the clustering could, in principle, be a statistical fluke or the result of some unknown bias in how the distant objects had been discovered. But they also made it clear that every simulation they ran, every dynamical model they tested, kept pointing to the same conclusion: a planet, massive, distant, real. The reaction in the astronomy community was mixed. Some researchers were immediately convinced. The clustering was too tight, the dynamical argument too clean. Others were skeptical. 6 objects, they pointed out, is a very small sample. Trans-Neptunian objects are hard to find. They're faint, they move slowly, and surveys capable of detecting them cover only tiny patches of sky. The apparent clustering could be an artifact of where and when astronomers happen to be looking. Observational bias, in other words, not evidence of a real planet. That criticism has been the most persistent line of attack against the Planet 9 hypothesis. If the objects were discovered by surveys that preferentially searched certain regions of sky at certain times of year, and if those regions happen to align with where objects on clustered orbits would be brightest, then the clustering isn't a mystery, it's a selection effect. You found what you were most likely to find, and the absence of objects in other parts of the sky just means nobody looked there yet. Batygin and Brown anticipated that objection. They ran simulations to test whether observational bias alone could explain the clustering. Their conclusion was no, even accounting for the known biases in how trans-Neptunian objects are discovered, the clustering remains statistically significant. Other teams ran their own simulations and came to different conclusions. Some found that bias could indeed produce clustering that looked like Planet 9's signature. Others confirmed that the effect was too strong to dismiss. The field split into camps: believers, skeptics, and a large middle group waiting for more data. The hunt expanded. More surveys began targeting the outer solar system. More trans-Neptunian objects were discovered, and the pattern held. By 2019, Batygin and Brown published an updated analysis. They had refined their model, incorporated new objects, and adjusted their estimate of Planet 9's properties. The preferred mass dropped slightly, settling around 5 Earth masses. The orbit tightened a bit, with the semi-major axis now estimated at roughly 400 to 500 astronomical units, but the core prediction didn't change. A planet out there shaping the distant solar system through gravity alone. And it wasn't just the clustering. Planet 9, if it exists, explains other puzzles too. There's a population of trans-Neptunian objects whose orbits are tilted almost perpendicular to the plane of the solar system. These objects loop up and over the sun's poles in paths that shouldn't exist if the only gravitational influences were the 8 known planets. Batygin and Brown's simulations showed that Planet 9 could tilt those orbits naturally over millions of years. The planet's gravity doesn't just cluster objects in one plane, it sculpts the entire outer solar system into a configuration that matches what we observe. There's also the obliquity problem. The sun's equator is tilted about 6 degrees relative to the plane of the planets. That tilt has never been fully explained. In a solar system that formed from a spinning disk of gas and dust, everything should be more or less aligned. Planet 9's orbit, tilted and distant, could torque the entire solar system over billions of years, producing exactly the 6-degree offset we measure today. Each additional puzzle that Planet 9 solves makes the hypothesis harder to ignore. And each additional trans-Neptunian object discovered with an orbit that fits the pattern tightens the statistical argument. By late 2024, the clustering significance had been recalculated multiple times by independent teams. One widely cited analysis put the confidence level at 99.6%, meaning there's less than a 0.5% chance the clustering is random. But here's the thing, confidence levels don't matter if the sample is biased, and the sample is small. As of this writing, fewer than a dozen objects meet the criteria for extreme detachment and orbital clustering that Planet 9 is supposed to explain. If even a few of those objects were discovered because of survey bias, the entire statistical case wobbles. This is the central tension. The evidence is tantalizing, the physics is sound, the simulations are consistent, but the telescope hasn't seen the planet. And until it does, Planet 9 remains a hypothesis, an extraordinarily well-motivated hypothesis backed by some of the best planetary dynamicists in the world, but still a hypothesis. There is another historical parallel worth noting. Neptune was predicted to explain irregularities in Uranus's orbit. Those irregularities were real, the math worked, the planet was found, but Pluto was predicted for the same reason. Those irregularities turned out not to be real, the math didn't work. The planet was found anyway, by accident, and then later demoted, so the precedent cuts both ways. Sometimes the invisible planet is there, sometimes it isn't. And sometimes you find something but it's not what you thought it was. That possibility hangs over the entire Planet 9 search. What if the clustering is real, but the explanation isn't a planet? What if it's something else? A passing star that disrupted the outer solar system billions of years ago. A temporary gravitational perturbation that left a fossil signature in the orbits of distant objects. Or something stranger, something that wouldn't show up in a telescope at all. For now, the search continues. Surveys are scanning the sky. Supercomputers are running simulations. And every few months, a new trans-Neptunian object is discovered and its orbit is measured. Each new data point either strengthens the case or weakens it. The next object could tip the balance, or it could take decades. Planet 9, if it's out there, is not making this easy. It's faint, it's far, and it's moving through a region of sky so large that even the best search programs can only cover a fraction of it in a reasonable amount of time. But the gravitational breadcrumbs are there, faint, scattered, but unmistakably pointing outward into the dark. Something massive is out there. Something that has been quietly sculpting the outer solar system for billions of years. And whether it's a planet, a black hole, or something no one has thought of yet, the hunt to find it has only just begun. The math alone should have been enough to dismiss it. That's what makes this whole story so uncomfortable. You cannot usually predict the existence of a planet using 6 data points and expect the rest of the scientific community to take you seriously. 6 orbits, 6 distant frozen rocks drifting in the dark, each one discovered years apart by different surveys using different instruments. And from that tiny sample, Batygin and Brown stood up in 2016 and said, "We know where a hidden planet is, how heavy it is, and roughly how long it takes to orbit the Sun." The audacity of that claim is easy to miss if you don't understand how fragile the evidence looked on paper. Except the math kept working. Every time someone tried to break it, the numbers held. Every additional trans-Neptunian object discovered in the years since has either strengthened the pattern or at minimum refused to contradict it. And the technique they used to make the prediction, the actual mechanics of following gravitational breadcrumbs backward to an unseen source, is the same method that found Neptune in 1846. It worked then, it's working now. The difference is that Neptune was hiding 30 astronomical units from the Sun. Planet 9, if it exists, is hiding somewhere between 400 and 800. That's not a distance problem, that's a detection horizon problem. And it means we're hunting something we can barely hope to see with instruments designed for a solar system that ends at 50 AU. Start with what the orbits are actually doing. The 6 objects Batygin and Brown analyzed in their original 2016 paper all share a set of characteristics that shouldn't coincide by accident. Each one has a semi-major axis, the long radius of its elliptical orbit, greater than 150 astronomical units. Each one has a perihelion, the closest point to the Sun, beyond 30 AU. That second condition matters because it places them outside Neptune's direct gravitational reach. Neptune orbits at 30 AU. Anything that comes closer than that can be scattered, nudged, or flung outward by a close encounter with the ice giant. These 6 objects never get that close. They are dynamically detached. Neptune didn't put them where they are, and yet their orbits are aligned. Not perfectly, but far more than random chance would predict. The angle that describes where each orbit reaches perihelion, called the argument of perihelion, clusters within a narrow range. 5 of the 6 original objects had arguments of perihelion between roughly 0 and 60 degrees. The 6th sat near 300 degrees, but even that outlier fit within a broader pattern when you account for how the orbits are tilted. All 6 orbits are inclined relative to the plane of the solar system, but the direction of those tilts, the orientation of the orbital planes themselves, also shows alignment. If you plotted these orbits in 3 dimensions, they would all point in roughly the same direction, like a set of arrows launched from different heights but aimed at the same target. The probability of that happening by chance is less than 1%. Batygin and Brown calculated it explicitly. If trans-Neptunian objects were scattered randomly into the outer solar system by the known planets, you would expect their orbits to be oriented randomly as well, some pointing here, some pointing there, no pattern. What they found instead was a pattern strong enough that ignoring it required assuming you'd just witnessed a 1 in 100 fluke. Possible, yes. Comfortable, no. So they built a model. Not a vague hypothesis. A detailed dynamical simulation of the outer solar system with an additional planet included. They tested thousands of configurations, different masses, different orbital shapes, different inclinations, different starting positions, and they asked a simple question: which configuration, if any, reproduces the clustering we see? The answer that kept coming back pointed to a planet roughly 5 to 10 times the mass of Earth, orbiting the Sun on a highly elliptical path with a semi-major axis between 400 and 700 AU. The orbit would be tilted about 15 to 25 degrees relative to the plane of the inner planets. And critically, the planet's own perihelion, the point where it comes closest to the Sun, would sit roughly 180 degrees opposite the perihelion cluster of the distant objects, anti-aligned. The planet's orbit and the orbits of the objects its shaping point in opposite directions. That anti-alignment is not a bug. It's the signature. When a massive distant planet orbits the Sun on a tilted, elongated path, it exerts a slow torque on anything smaller that crosses its gravitational influence. Over millions of years, that torque nudges the smaller objects into a stable configuration where their orbits avoid direct collisions with the planet. The way to avoid a collision is to reach perihelion, the moment when you're moving fastest and closest to the Sun, at the exact opposite point in space from where the planet reaches its own perihelion. You're on opposite sides of the solar system. Your orbits may cross in terms of distance, but they never cross in time. The objects slip past each other like trains on parallel tracks scheduled never to meet. This is called a mean motion resonance, and it's one of the most common ways gravity organizes orbits over long timescales. The moons of Jupiter are locked in resonances with each other. The asteroid belt has gaps carved out by resonances with Jupiter. The Kuiper belt itself has a population of objects, including Pluto, locked in a 3-to-2 resonance with Neptune. Resonances are everywhere. They're just usually obvious because the massive object doing the organizing is easy to see. Here, the organizing object is invisible, but its fingerprints are all over the data. Batygin and Brown didn't stop at the clustering. They looked at other populations of trans-Neptunian objects that had puzzled astronomers for years and asked whether Planet 9 could explain those too. One particularly strange group consists of objects with orbits tilted almost perpendicular to the plane of the solar system. These are the high-inclination outliers, objects that loop up and over the Sun's poles in paths that shouldn't exist if the only gravitational influences are the 8 known planets. There's no mechanism in the standard model of solar system formation that would tilt an object that dramatically, and yet there they are. At least half a dozen confirmed, probably more waiting to be found. Planet 9 explains them. In the simulations, the distant planet's gravity doesn't just cluster objects in one plane, it sculpts the entire outer solar system into a three-dimensional structure. Some objects get their orbits twisted into perpendicular configurations. Others get flipped entirely, ending up on retrograde orbits that circle the Sun in the opposite direction from everything else. Mike Brown has called these high-inclination objects nearly impossible to explain without Planet 9, and he's not exaggerating for effect. There is no competing theory that predicts them, none. You either accept that a distant massive planet is carving up the outer solar system, or you accept that a bunch of extremely weird orbits showed up for reasons no one can articulate. The updated models published in 2019 refined the estimates and tightened the constraints. By then, additional trans-Neptunian objects had been discovered that fit the clustering pattern, bringing the total count to more than a dozen. The statistical significance climbed. The preferred mass for Planet 9 dropped slightly, settling closer to 5 Earth masses rather than 10. The semi-major axis estimate tightened to around 400 to 500 AU. The eccentricity, a measure of how elongated the orbit is, was estimated at roughly 0.2 to 0.5. 0 would be a perfect circle. 1 would be a parabola that never closes. Planet 9's orbit is elliptical, but not extremely so. It swings in and out, but it stays bound to the Sun. The inclination estimate held steady at 15 to 25 degrees. That tilt is important, because it helps explain another long-standing puzzle. The Sun's equator is tilted about 6 degrees relative to the orbital plane of the planets. Nobody has ever fully explained why. In a solar system that formed from a flat spinning disk of gas and dust, you'd expect everything to be aligned. The Sun should spin in the same plane the planets orbit. It doesn't. It's off by 6 degrees. And that offset has been sitting in the data since the early days of astronomy, with no satisfying explanation. Planet 9, with its tilted orbit and long lever arm, could torque the entire inner solar system over billions of years. The simulations show that a 5 Earth mass planet on the predicted orbit would produce exactly the 6-degree tilt we observe. Not approximately, exactly. Every time Planet 9 solves another puzzle, the hypothesis gets harder to dismiss, and the list of puzzles it solves keeps growing. There's the perihelion distribution. If Neptune were the only thing shaping the outer Kuiper belt, you'd expect a sharp cutoff in the number of objects with perihelia, closer than about 40 AU. Closer than that, and Neptune's gravity would dominate, scattering objects into different orbits or ejecting them entirely. Instead, the observed distribution shows a smooth decline. Objects with perihelia at 35 AU, 40 AU, 45 AU, all the way out. The drop-off is gradual, not sudden. Brown pointed this out in 2017. The smooth decline matches what Planet 9's simulations predict. The planet's distant gravity gently shepherds objects across a range of perihelion distances without producing a hard edge. Then there's the population inside Neptune's orbit. In 2021, Batygin and collaborators published simulations showing that Planet 9's influence isn't limited to the distant Kuiper belt. The planet's gravity, acting over millions of years, would also perturb objects much closer in, asteroids, centaurs, even some comets. The perturbations are tiny at that range. Planet 9 is far away, and gravity weakens with distance. But over geologic time, tiny perturbations add up. The team ran hundreds of thousands of simulations, tracking how a distant planet would affect inner solar system objects. The results matched observed orbital distributions better than models without Planet 9. That's not proof, but it's another breadcrumb. The concept driving all of this is called orbital precession. Every orbit precesses. That means the orientation of the orbit slowly rotates over time. Picture an ellipse drawn on a piece of paper. Now imagine the entire ellipse rotating clockwise, keeping its shape but changing which direction it points. That's precession. It happens because no orbit exists in isolation. Every planet tugs on every other planet. Every large object exerts a small gravitational pull on everything nearby. The result is that orbital parameters drift, slowly, predictably, and in ways that can be calculated. Precession happens around the barycenter, the center of mass of the system. For a single planet orbiting the Sun, the barycenter sits very close to the Sun's center because the Sun is so much more massive. But when you add more planets, the barycenter shifts slightly, and the precession rate of any given orbit depends on the distribution of mass in the system. If there's a hidden massive object pulling from a particular direction, that object's gravity will add a systematic bias to the precession. Orbits won't drift randomly. They'll drift in a coordinated way, all responding to the same unseen pull. That's what Batygin and Brown saw in the data. The orbits of distant trans-Neptunian objects weren't just clustered in space. They were clustered in a way that indicated their precession had been influenced by the same source. The simulations showed that a 5 to 10 Earth mass planet on an anti-aligned orbit would naturally produce that kind of clustering. Over millions of years, the planet's gravity would nudge the smaller objects into a configuration where their perihelia all pointed away from the planet's perihelion, and once that configuration formed, it would be stable. The objects would stay clustered because the resonance protects them from scattering. This is why the hypothesis has survived for nearly a decade despite the absence of direct observation. The prediction isn't just that a planet exists, it's that a planet of a specific mass in a specific orbit would produce a specific set of observable effects, and those effects keep showing up. New trans-Neptunian objects are discovered every year. Some of them fit the pattern, some don't. But the ones that do fit continue to strengthen the statistical case. By 2024, some analyses put the confidence level at 99.6%. That means the odds of the clustering being a random coincidence are less than 0.5%, but confidence levels are only meaningful if the sample is unbiased, and that's where the whole argument gets messy. Trans-Neptunian objects are hard to find. They're faint, they move slowly across the sky. Surveys capable of detecting them are limited by telescope time, weather, and the simple fact that the sky is enormous and these objects occupy a tiny fraction of it. Most surveys target specific regions of the sky at specific times of year, and if those regions happen to overlap with where objects on clustered orbits would be brightest, then the apparent clustering isn't evidence of a planet. It's evidence of where astronomers pointed their telescopes. This is the observational bias critique, and it's the main reason the Planet 9 hypothesis remains controversial. Some researchers argue that the clustering is real and robust even after accounting for survey biases. Others argue that the sample size is too small and too biased to draw any strong conclusions. The difference between those two positions comes down to how you model the bias. Do you trust the orbital distribution as observed, or do you assume that significant parts of the distribution are missing because nobody has looked there yet? Both sides have published papers, both sides have run simulations, and they arrive at different answers. Batygin and Brown have consistently argued that the clustering is not an artifact of bias. They've tested multiple scenarios, accounting for known survey strategies and detection thresholds. In every test, the clustering remains significant. Other teams, particularly those skeptical of Planet 9, have run their own tests and found that bias could account for the pattern. The disagreement has become one of the defining features of the debate, not whether the math is right, Everyone agrees the math is right. The question is whether the data going into the math represents reality or a distorted sample. There's another layer to this. Even if the clustering is real, even if observational bias can't explain it, that doesn't automatically mean Planet 9 is the answer. It just means something is causing the clustering. A distant planet is one explanation, but there are others. A passing star could have disrupted the outer solar system billions of years ago, scattering objects into aligned orbits that have persisted ever since. A temporary disk of material in the early solar system could have exerted enough collective gravity to organize distant orbits before dispersing. Or the clustering could be a transient feature, something that looks significant now but will dissolve as more objects are discovered. Each of those alternatives has problems. A passing star would need to have come extremely close enough to perturb distant Kuiper belt objects, but not so close that it disrupted the inner planets. The timing would need to be just right. And there's no evidence in the stellar neighborhood of a close encounter in the last few billion years. A primordial disk could work, but it would need to have been massive and long-lived, and it would need to have left no other trace in the solar system's architecture. Possible, maybe. Likely, no. The transient clustering idea is harder to rule out, but it requires assuming that we just happen to be observing the solar system during a brief window when random processes produced an alignment that will disappear in another few million years. That's not impossible. It's just uncomfortable. It means the most interesting feature of the outer solar system is an accident of timing. Planet 9, by contrast, is a permanent explanation. If the planet exists, it's been shaping the outer solar system for billions of years and will continue to do so for billions more. The clustering isn't a temporary accident. It's a stable, dynamical structure maintained by an ongoing gravitational influence. That makes Planet 9 testable in a way the other explanations aren't. Find the planet, and the hypothesis is confirmed. Fail to find it after exhaustively searching the predicted region, and the hypothesis is ruled out. Clean, falsifiable, the way science is supposed to work. The hunt is constrained by the predictions. Planet 9's orbit is enormous. At 400 to 800 AU, the planet could be anywhere in a huge swath of sky. And because the orbit is elliptical, the planet spends most of its time at the far end of that ellipse, where it's faintest. Surveys searching for Planet 9 have to cover thousands of square degrees. They have to go deep enough to detect an object that might be as faint as magnitude 22 or dimmer, and they have to do it repeatedly because the only way to confirm an object is a planet rather than a background star or a distant galaxy is to watch it move. Several surveys are underway. The Zwicky Transient Facility in California scans large areas of the northern sky every few nights. The Dark Energy Survey, originally designed to study distant galaxies, has produced deep images of the southern sky that can be searched for moving objects. The upcoming Vera Rubin Observatory, scheduled to begin full operations in the mid-2020s, will survey the entire visible sky every few nights with unprecedented depth and coverage. If Planet 9 is out there and bright enough, Rubin will find it. But there's a catch. If Planet 9's mass is on the lower end of the estimates, closer to 5 Earth masses, and if it's currently near the far end of its orbit, it could be too faint for even Rubin to detect. The brightness of a planet depends on how much sunlight it reflects and how far it is from both the Sun and Earth. At 800 AU, Planet 9 would be receiving only a tiny fraction of the sunlight that reaches Earth, and the light it reflects would have to travel 800 AU back to us. By the time it arrives, the planet would be extraordinarily dim. Some estimates put it near the limit of what current ground-based telescopes can see. Others suggest it's just beyond that limit. That creates a frustrating scenario. The evidence points to a planet. The simulations work. The clustering holds, but the planet might be hiding in a region of parameter space where detecting it requires either an enormous amount of luck or a telescope that doesn't exist yet, or both. And until someone finds it, the hypothesis remains exactly that, a hypothesis, compelling, well-motivated, supported by a decade of research, but still unconfirmed. The anti-aligned population adds another layer of evidence. These are trans-Neptunian objects whose orbits point in the opposite direction from the main clustering. Instead of having perihelia clustered near 0 to 60 degrees, their perihelia sit near 180 to 240 degrees. The simulations predict that Planet 9 should produce both populations, objects that get captured into the same resonance as the main cluster, and objects that get captured into the opposite phase of the resonance. Both groups avoid the planet by reaching perihelion at times when the planet is far away. One group does it by staying on one side of the solar system. The other group does it by staying on the opposite side. Observations have confirmed that both populations exist. The anti-aligned objects are fewer in number, which matches the predictions. The resonance is slightly less stable in the anti-aligned configuration, so fewer objects survive there over billions of years. But the fact that they exist at all and that their distribution matches what Planet 9 predicts is yet another breadcrumb pointing in the same direction. So here's where we are. A decade of simulations, more than a dozen trans-Neptunian objects with extreme orbits, statistical confidence above 99% in some analyses, and a set of predictions specific enough to be tested. Planet 9, if it exists, weighs about 5 to 10 times as much as Earth, orbits the Sun every 10,000 to 20,000 years, and sits somewhere between 400 and 800 AU from the Sun on an orbit tilted 15 to 25 degrees out of the plane. Its perihelion is anti-aligned with the clustering of distant Kuiper belt objects. Its gravity explains high inclination orbits, retrograde orbits, the tilt of the Sun's equator, and the smooth perihelion distribution of the outer solar system. Every single one of those predictions is testable. Every single one can be checked against future observations, and every single one has held up so far. The math works, the physics works. The only thing missing is the planet itself. And somewhere out there, in a patch of sky too large to search quickly and too dark to see easily, a world 10 times the mass of Earth may be drifting through the void, shaping the solar system with nothing but gravity and time. The breadcrumbs lead there. Now someone just has to follow them far enough to see what's waiting at the end. The gravitational breadcrumbs were enough to start the conversation. They weren't enough to end it. By 2020, Planet 9 had survived 4 years of scrutiny, replication attempts, and statistical arguments that would have killed most hypotheses before they reached their second birthday. The clustering held, the simulations kept working, but nobody had seen the planet. And in astronomy, a theory without an observation is just math waiting to be proven wrong. Then something unexpected happened. Astronomers stopped looking only at orbits and started looking at light. Not reflected sunlight, which is what you'd normally use to spot a planet. Infrared light. The kind of radiation that cold objects emit simply by existing. And in archival images taken decades apart by a Japanese telescope most people had never heard of, they found something that shouldn't be there. The telescope is called Akari. It launched in 2006 as Japan's second infrared space observatory, designed to scan the entire sky in wavelength invisible to the human eye. Infrared sits just beyond the red edge of the visible spectrum. It's the light you feel as heat when you stand near a campfire. Everything with a temperature above absolute zero, emits infrared radiation. Hot things glow brightly in infrared, cold things glow faintly. But they still glow. Akari's job was to map that glow across the entire sky, looking for cool stars, dust clouds, distant galaxies, anything that shines in the thermal part of the spectrum. It operated for about a year and a half before its coolant ran out and the mission ended. The data sat in archives for more than a decade, mostly used by researchers studying star formation and interstellar dust. Nobody thought to search it for planets in our own solar system until recently. That oversight is understandable. Reflected sunlight is how we find planets. You point a telescope at a patch of sky, take an image, wait a few weeks or months, take another image, and look for something that moved. If it moved, it's probably orbiting the sun. Measure its motion, and you can calculate its orbit. Simple, reliable, proven. But reflected sunlight has a problem. The farther an object is from the sun, the less sunlight reaches it, and the dimmer it appears. Brightness falls off with the square of the distance. An object at 400 astronomical units receives 1,600 times less sunlight than Earth does, and the light it reflects has to travel all the way back to our telescopes, which means it dims again by another factor of 1,600. Total drop, over 2.5 million times fainter than it would be at Earth's distance. Planet 9, if it's out there near the far end of its orbit, is receiving almost no sunlight, and the tiny amount it reflects is arriving at Earth so faint that even the best ground-based telescopes are struggling to pick it out from the noise. Thermal emission bypasses that problem. A massive planet doesn't just reflect light, it generates its own heat, not from nuclear fusion like a star. Planets aren't hot enough for that, but from leftover heat from formation and from the slow gravitational compression of their interiors. Jupiter, for example, radiates more energy into space than it receives from the Sun. Saturn does the same. Both planets are still warm from the process that built them 4.5 billion years ago, and both glow in the infrared because of it. Planet 9, if it exists, should also glow. It's big enough, 5 to 10 Earth masses, that it would retain significant internal heat even after billions of years. And unlike reflected sunlight, which dims with distance twice, thermal emission only dims once. The planet radiates. That radiation travels to Earth. The intensity drops with the square of the distance, yes, but there's no second dimming from the sun's distance to the planet. You're detecting the planet's own glow, not a reflection. That makes thermal emission potentially easier to detect at extreme distances than reflected light. Potentially. The problem is that a cold planet at 400 AU is still extraordinarily faint. Its surface temperature would be somewhere around 40 to 50 Kelvin. That's cold, colder than liquid nitrogen. The peak of its thermal emission would fall in the far infrared, at wavelengths around 60 to 100 micrometers. Most ground-based telescopes can't see those wavelengths at all. Earth's atmosphere absorbs them. You need a space telescope, or you need archival data from a space telescope that already scanned the sky years ago and didn't know what it was looking at. That's where Akari comes in. The telescope operated in multiple infrared bands, including the far infrared range, where a cold, distant planet would emit most strongly. And because it was an all-sky survey, it imaged essentially every part of the sky visible from its orbit. If Planet 9 crossed any of those fields during Akari's mission, the telescope might have seen it. Not as a resolved disk. At 400 AU, even a planet 5 times Earth's size would appear as a point source, indistinguishable from a distant star or galaxy in a single image. But if you compare images taken years or decades apart, a planet moves, stars don't, galaxies don't. The background stays fixed. The planet drifts. A team of researchers led by astronomers in Japan and the United States dug into the Akari archives and cross-referenced them with data from an earlier infrared mission called ERAS, the Infrared Astronomical Satellite, which flew in 1983. ERAS also scanned the sky in far infrared wavelengths. The two missions were separated by 23 years. Anything that moved between 1983 and 2006 would show up as a source that appeared in one location in the IRAS data and a slightly different location in the Akari data. The team built an algorithm to search for exactly that kind of motion. Slow, steady, consistent with an object orbiting the Sun at a few hundred astronomical units. They found candidates, not dozens, a handful. Faint infrared sources that appeared in both surveys but had shifted position by an amount consistent with a distant solar system object. Most of them were easy to rule out. Background galaxies that happened to have variable brightness, asteroids closer in that were misidentified, instrumental noise. But one or two sources resisted easy explanation. Faint, slow-moving, sitting in a region of sky that overlapped with the predicted orbit of Planet 9. The results were published cautiously. The authors did not claim they had found the planet. They claimed they had found candidates worth following up. The data quality from both IIS and Akari wasn't high enough to confirm a discovery on its own. The sources were at the edge of detectability. The position measurements had error bars large enough that pinning down an exact orbit was impossible, but the fact that anything showed up at all, in the right part of the sky, moving at roughly the right speed, was enough to get attention. This is what weak signals look like, not smoking guns, whispers. An anomalous dot in a decades-old image that might be noise, might be a background object, or might be the first thermal detection of a planet no one has ever seen. Follow-up observations are the only way to know for sure. Point a modern infrared telescope at the candidate positions and see if anything is still there. If it is, and if it has moved in a way consistent with a bound orbit around the Sun, then the whisper becomes a shout. As of now, those follow-up observations are either still underway or haven't been made public. The Akari candidates remain exactly that, candidates. Intriguing, yes. Confirmed, no. But they represent a shift in strategy. For the first time, astronomers are hunting Planet 9 not by where it pulls, but by what it emits. That opens up new search methods. Telescopes designed for cosmology, for studying distant galaxies and the early universe, can be repurposed to scan the outer solar system for faint infrared sources. Archival data from other missions can be combed for slow-moving objects that were ignored the first time around because nobody was looking for them. And the search isn't limited to infrared. Some researchers have proposed looking for Planet 9 in radio wavelengths. A cold planet wouldn't emit strongly in radio, but if it has a magnetic field and that field interacts with the solar wind, it could produce faint radio bursts detectable by large arrays like the Very Large Array in New Mexico or ALMA in Chile. Others have suggested searching for the planet's shadow. If Planet 9 passes in front of a distant star, it would block the star's light for a brief moment, producing a dip in brightness that could be measured. This technique, called occultation, has been used to study asteroids and Kuiper Belt objects. Scaling it up to hunt for a planet requires monitoring thousands of stars simultaneously and catching the occultation in real time. Hard, but not impossible. Each method has limitations. Infrared searches depend on the planet being warm enough to glow and close enough that the glow reaches detectable levels. Radio searches depend on the planet having an active magnetosphere. Occultation searches depend on the planet passing directly between Earth and a background star, which is statistically rare given how much sky there is to cover. But the fact that multiple independent methods are converging on the same prediction is what makes the hypothesis robust. You're not relying on one technique or one dataset. You're building a case from every angle the data allows. Then there are the new objects. Trans-Neptunian objects are still being discovered at a steady pace. Most of them have ordinary orbits, circular, aligned with the plane of the solar system, entirely consistent with the known architecture of the Kuiper belt. But every few years, a survey finds one that doesn't fit. An object with an orbit so extreme, so detached from Neptune's influence, that it demands an explanation. And each time one of those objects shows up, astronomers check whether its orbit matches the pattern Planet 9 predicts. More often than not, it does. The process works like this. A survey, usually a wide-field telescope scanning large sections of sky night after night, picks up a faint moving dot. The dot is flagged as a potential trans-Neptunian object based on its motion. Follow-up observations over the next several months or years refine the orbit. Once the orbit is well determined, it gets added to the catalogue of known TNOs. Researchers then analyze the full catalogue, looking for patterns in the orbital elements, clustering in perihelion angle, clustering in inclination, anti-aligned orbits, high inclination outliers. Every new object either strengthens the existing patterns or dilutes them. So far, the patterns have held. A 2017 study led by Carlos and Raúl de la Fuente Marcos analyzed the orbits of extreme trans-Neptunian objects and found that their ascending node distances, the points where their orbits cross the plane of the solar system, clustered around 300 to 400 astronomical units. That's exactly the range where Planet 9's gravity would be strong enough to organize orbits. The authors tested whether the clustering could be explained by observational bias, the idea that surveys were simply more likely to find objects in certain parts of the sky and at certain times of year. Their conclusion was blunt. They wrote that they believe what they are seeing cannot be attributed to the presence of observational bias. The clustering, in their view, is real. And the only explanation that fits is a distant, massive planet. Not everyone agrees. Other teams have run similar tests and concluded that bias could account for the pattern. The argument hinges on how you model the surveys. If you assume the surveys are roughly uniform in their coverage, then the clustering stands out. If you assume the surveys have significant blind spots and selection effects, then the clustering might be an artifact. The debate hasn't been settled, but the fact that new objects keep showing up in the predicted configuration is at minimum uncomfortable for the bias explanation. If the clustering were purely an artifact of where telescopes happen to point, you'd expect it to dissolve as more sky gets covered. It hasn't dissolved, it's gotten tighter. One particularly interesting development is the discovery of objects on retrograde orbits. These are trans-Neptunian objects that orbit the Sun in the opposite direction from everything else in the solar system. Retrograde orbits are extremely rare. The standard model of solar system formation doesn't produce them. Everything should be orbiting in the same direction because everything formed from the same rotating disk of gas and dust. A retrograde orbit means something flipped the object's trajectory entirely. Planet 9 can do that. The simulations show that a distant massive planet on a tilted orbit can gradually flip the orbits of smaller objects over millions of years, turning prograde orbits into retrograde ones. It's not a common outcome. Most objects don't get flipped, but a few do, and those few should be detectable. Observers have found them. Not many, a handful, but their existence is hard to explain without invoking Planet 9. Some researchers have proposed that retrograde TNOs could have been captured from interstellar space, rogue objects that wandered into the solar system and got gravitationally bound. That explanation works for one or two objects. It doesn't work for a population. The odds of capturing multiple interstellar objects into stable orbits around the Sun are vanishingly small. Planet 9, by contrast, predicts that a small fraction of the trans-Neptunian population will end up on retrograde orbits as a natural consequence of the planet's gravitational influence. The prediction matches the observations. That's not proof, but it's another breadcrumb. The recalibration of solar system maps is worth dwelling on because it illustrates how much the search has narrowed. When Batygin and Brown first proposed Planet 9 in 2016, the predicted region of sky was enormous, hundreds of square degrees. The planet could have been almost anywhere along its orbit. Surveys started scanning those regions systematically, and as they scanned, they ruled out chunks of the search space. Not because they found the planet, because they didn't find it. If Planet 9 were in a given patch of sky and brighter than a certain threshold, the surveys would have seen it. They didn't. So that patch gets crossed off. The process is slow. Each survey only covers a fraction of the total area. But over the course of several years, the excluded regions add up. By some estimates, about 78% of the predicted region has now been searched to sufficient depth that Planet 9, if it's there and near the brighter end of the estimated brightness range, should have been detected. It wasn't. That leaves about 22% of the predicted region still unsearched. Either the planet is hiding in that remaining 22%, or it's fainter than the surveys can currently detect, or it doesn't exist. The fact that 78% has been ruled out sounds discouraging. It's actually the opposite. It means the search is working. The predictions were specific enough that they could be tested. The tests have eliminated most of the possibilities. What's left is a much smaller, much more focused target. Future surveys know exactly where to look. The Vera Rubin Observatory is the instrument most likely to settle this. It's a ground-based telescope in Chile designed to scan the entire southern sky every few nights with unprecedented depth and speed. Rubin is optimized for detecting moving objects. Asteroids, comets, trans-Neptunian objects, anything that shifts position between images. If Planet 9 is anywhere in the southern sky and brighter than magnitude 24, Rubin will find it within a few years of starting operations. The telescope is scheduled to begin its main survey in the mid-2020s. The timeline is tight but realistic. By 2030, if Rubin hasn't found Planet 9, the hypothesis will be in serious trouble. Some astronomers are already preparing for that possibility. If the searches come up empty, it doesn't necessarily mean the clustering is fake or the math is wrong. It could mean the planet is fainter, smaller, or farther than the current estimates predict. A 3-Earth mass planet at 800 AU would be extraordinarily difficult to detect even with Rubin. It would still produce the same gravitational effects. The clustering would still be there, but the planet itself might remain invisible for another generation of telescopes. That's a frustrating scenario. The evidence points to something real. The something refuses to show itself. There's also the possibility that the something isn't a planet at all. This is where the alternative explanations start to look more plausible. If Planet 9 is too faint to detect after exhaustive searches, maybe the gravitational effects are being caused by something else. Something that doesn't emit or reflect light in the way a planet would. A primordial black hole, for example, or a clump of dark matter. Both possibilities have been proposed in peer-reviewed papers. Both sound absurd until you look at the math and realize they're not obviously wrong. A primordial black hole is a black hole that formed in the first fractions of a second after the Big Bang, created by density fluctuations in the early universe rather than the collapse of a star. If one of those black holes happened to be captured by the sun's gravity billions of years ago, it would orbit just like a planet. It would have mass. It would pull on nearby objects. It would produce exactly the kind of clustering that Planet 9 predicts, and it would be completely invisible. Black holes don't emit light unless they're actively feeding. A small black hole drifting through the outer solar system would be silent, dark, and undetectable by any conventional telescope. The only way to find it would be through its gravitational effects, which we're already seeing, or through extremely exotic detection methods like looking for gravitational lensing or bursts of radiation from matter falling into the black hole. Dark matter is even stranger. If dark matter particles can clump together under their own gravity, and if a clump of dark matter got captured into a solar orbit, it would act like a planet without being one. It would have mass, it would pull, it would organize orbits, and it would be invisible to every instrument we have because dark matter doesn't interact with light. The hypothesis is speculative. Most dark matter models don't predict clumps stable enough to behave like a bound object, but some do, and if one of those clumps is sitting in the outer solar system, it would explain the gravitational evidence without requiring a planet. Both ideas, primordial black holes and dark matter clumps, are considered long-shot alternatives. They're not the preferred explanation, but they're on the table because the gravitational evidence is strong enough that dismissing it entirely is no longer an option. Something is out there. If it's not a planet, it's something weirder. And if it's something weirder, the discovery would be far more significant than finding another planet. A primordial black hole in our own solar system would be the first direct detection of an object from the earliest moments of the universe. A dark matter clump would be the first confirmed detection of dark matter in any form. Either discovery would rewrite textbooks. For now, the evidence tilts toward a planet. The simplest explanation, the one that requires the fewest new assumptions, is that a 5 to 10 Earth mass world is drifting through the outer solar system on a long, slow orbit. The Akari candidates, the retrograde TNOs, the clustering that refuses to go away, all of it points in that direction. The whispers are faint. They're scattered across different datasets, different wavelengths, different observation techniques, but they're converging. Every new piece of evidence that shows up either fits the Planet 9 hypothesis or at minimum doesn't contradict it. And the searches are getting better. The telescopes are getting sharper. The surveys are covering more sky. The timeline for an answer is shrinking. Within the next few years, one of three things will happen. Rubin or another survey will find Planet 9 directly, confirming the hypothesis and giving us the first images of a world that has been hiding since the solar system formed. Or the searchers will exhaust the predicted region without finding anything, forcing a recalibration of the hypothesis or an admission that the clustering is an artifact we don't yet understand. Or the searchers will find something else entirely, something that produces the gravitational signature of a planet but isn't one. A black hole, a dark matter clump, or some other object that doesn't fit into any existing category. All three possibilities are uncomfortable in their own way. Finding Planet 9 would mean our solar system is bigger and stranger than we thought. Failing to find it would mean the most compelling orbital evidence in modern planetary science led nowhere. And finding something else would mean the outer solar system is hiding objects we didn't think could exist. There's no safe answer. Every outcome reshapes what we thought we knew. And standing at the edge of that uncertainty, staring into a dataset that keeps whispering the same message from a dozen different directions, the only honest conclusion is that something is waiting out there, something massive, something real, something that has been shaping the architecture of the solar system for billions of years while humanity looked the other way. The whispers are getting louder, and sooner or later they're going to resolve into a shout. The whispers are converging, the orbits are clustering, the math keeps working, and every new trans-Neptunian object that shows up in the predicted configuration tightens the statistical noose around the idea that something massive is hiding in the outer solar system. For most astronomers, that something is a planet, 5 to 10 times Earth's mass, drifting through the void on a 10,000-year orbit, too faint to see but heavy enough to reshape everything around it. The hypothesis is elegant, it fits the data, it's testable, and it's probably wrong. Not wrong about the gravitational effects. Those are real. The clustering is real. The high inclination orbits are real. The anti-aligned population is real. Something is pulling on the outer solar system with enough force to organize dozens of objects into a coordinated pattern that has persisted for millions of years. The question isn't whether something is out there, the question is what that something is, and a growing number of researchers are starting to suspect that the answer isn't a planet at all, it's something far stranger, something that doesn't reflect sunlight, doesn't glow in infrared, and doesn't belong to any category of object humanity has ever directly observed. A primordial black hole. That phrase lands like a punchline at first. Black holes are supposed to live at the centers of galaxies or in the collapsing cores of dying stars. They weigh millions or billions of solar masses, they warp space-time into knots, and they sit light-years away from anything we care about. The idea that one could be orbiting our sun, closer than the nearest star, smaller than a cantaloupe but heavier than Jupiter, sounds like science fiction written by someone who doesn't understand the genre. Except the math doesn't laugh, the physics doesn't laugh. And when you run the numbers on what a small black hole would do if it happened to be drifting through the outer solar system, the answer you get back looks disturbingly similar to the evidence we've been staring at for the last decade. Start with what a primordial black hole actually is. The name describes when it formed, not how big it is. Primordial means it came from the early universe, not from a star, not from a supernova. From the chaotic first moments after the Big Bang, when the universe was still a seething soup of energy and matter, packed into a volume far smaller than it occupies today. In those first fractions of a second, density fluctuations, tiny random variations in how tightly matter was packed in different regions, could have collapsed under their own gravity before the expanding universe smoothed them out. If a fluctuation was dense enough and compact enough, it wouldn't just clump into a cloud of gas, it would collapse all the way down into a black hole. No fusion, no starlight, no billion-year wait for a massive star to exhaust its fuel. Just instant gravitational collapse in the first microseconds of cosmic history. The process is hypothetical. Nobody has ever confirmed it happened, but the physics allows it. And if it happened, the black holes it produced could have any mass ranging from microscopic, lighter than a grain of sand, up to hundreds of thousands of solar masses. The smaller ones would have evaporated almost immediately through Hawking radiation. The larger ones would still be around today, drifting through the universe as invisible relics of a time when space-time itself was still settling into the structure we recognize. The interesting range for this story sits right in the middle, a few Earth masses to a few dozen Earth masses, small enough to be compact, large enough to survive billions of years without evaporating, and exactly the mass range that Planet 9 is supposed to occupy. A black hole with a mass of 10 Earths would have an event horizon, the boundary inside which nothing can escape, with a radius of about 9 centimeters, roughly the size of a grapefruit. Not the black hole itself. There is no itself in the usual sense. The mass would be concentrated at a singularity, a point of infinite density at the center. But the event horizon, the region of no return, would be 9 centimeters across. You could hold it in your hands if your hands could survive the tidal forces, which they couldn't. Stand a meter away and you'd be torn apart by the difference in gravitational pull between your head and your feet. Stand 10 meters away and you'd feel a tug roughly equal to Earth's gravity. Stand 1,000 kilometers away and the black hole would look, gravitationally speaking, identical to a planet of the same mass. That's the key insight. From a distance, mass is mass. A 10 Earth mass planet and a 10 Earth mass black hole exert the same gravitational pull on anything orbiting around them. The orbits of distant Kuiper belt objects wouldn't know the difference. They respond to gravity. They don't care whether the gravity comes from rock and gas or from a singularity wrapped in an event horizon. If you swapped Planet 9 for a primordial black hole of the same mass sitting in the same orbit, the clustering would stay exactly the same. The high inclination objects would stay tilted. The retrograde orbits would stay retrograde. Every prediction that Planet 9 makes, a primordial black hole makes too. The difference is visibility. A planet, even a cold one at 800 astronomical units, reflects a tiny amount of sunlight. It also radiates its own heat, faint thermal emission left over from its formation. Both of those signals are detectable in principle. Faint, yes, at the edge of what current instruments can see, yes, but detectable. A primordial black hole produces neither. It doesn't reflect light because it's smaller than a beach ball, and because any light that hits the event horizon gets absorbed. It doesn't radiate heat because it's not made of matter with a temperature. It's a knot in space-time. The only radiation it emits is Hawking radiation, a quantum mechanical effect where particle pairs spontaneously form near the event horizon and one particle falls in while the other escapes. For a black hole with a mass of 10 Earths, the Hawking radiation is so faint that it would take longer than the current age of the universe for the black hole to lose even a fraction of its mass. The power output is measured in trillionths of a watt. You would have a better chance of detecting the warmth from a firefly on the far side of the moon. So if a primordial black hole is sitting where Planet 9 is supposed to be, no telescope is going to see it the way we normally see planets. It's not glowing, it's not reflecting. It's not emitting anything we can measure with optical, infrared, or radio telescopes. The only way to know it's there is by watching what it does to everything around it. The gravitational effects, the clustering, the weird orbits, which is exactly what led to the Planet 9 hypothesis in the first place. The evidence doesn't distinguish between a planet and a black hole. Both are invisible. Both pull. The only difference is that one might eventually show up in a deep enough image, and the other never will. The idea that Planet 9 could be a primordial black hole was first proposed in a 2019 paper by Jakob Schultz, a physicist at Durham University in the UK, and James Unwin, a physicist at the University of Illinois at Chicago. The paper was careful. It didn't claim to have found a black hole. It pointed out that if the searches for Planet 9 keep coming up empty, and if the gravitational evidence remains strong, then a primordial black hole becomes a viable alternative explanation. The paper calculated what a 10 Earth mass black hole would look like from a detection standpoint. The answer was grim. Optical searches wouldn't find it. Infrared searches wouldn't find it. Reflected light searches wouldn't find it. The only plausible detection method was gravitational, either through direct observation of its effect on nearby objects, which is what the orbital clustering already represents, or through a phenomenon called microlensing. Microlensing happens when a massive object passes in front of a distant background star. The massive object's gravity bends the light from the star, briefly magnifying it. The star appears to brighten for a few hours or days as the lensing object moves across the line of sight. Then it dims back to normal as the object moves away. The effect is well understood, and has been used to detect planets around other stars, rogue planets drifting through the galaxy, and even clusters of dark matter. A 10-Earth mass black hole moving through the outer solar system would produce a micro-lensing signal if it happened to pass in front of a background star at the right time. The problem is that the outer solar system is enormous. The number of background stars bright enough to show a detectable lensing event is limited, and the black hole would need to pass directly in front of one of them within the narrow field of view of a telescope that happened to be watching at that exact moment. The odds are not good, but they're not zero. Schultz and Unwin calculated that a dedicated micro-lensing survey targeting the region where Planet 9 is predicted to orbit could detect a primordial black hole within a few years if the survey monitored enough stars and ran long enough. The survey would need to cover a few hundred square degrees of sky, watch millions of stars simultaneously, and repeat the observations every few nights to catch the brief brightening caused by the lensing event. That kind of survey is technically possible with current or near-future telescopes. It's also expensive, time-consuming, and requires a lot of luck. If the black hole is at the far end of its orbit, moving slowly, the chances of it crossing in front of a star during the survey window drop even further. But it's the best method anyone has come up with for finding an object that doesn't emit light and doesn't reflect it. The reaction to the primordial black hole hypothesis was mixed. Some astronomers welcomed it as a creative alternative that forced the field to think beyond conventional planet searches. Others dismissed it as unnecessarily exotic. Why invoke black holes from the early universe when a perfectly ordinary planet does the job just fine? The counter-argument is that the planet hypothesis has been tested for nearly a decade and hasn't produced a detection. 78% of the predicted search region has been surveyed, no planet. If Planet 9 were near the brighter end of its estimated brightness range, someone should have found it by now. The fact that nobody has suggests either the planet is fainter than expected, sitting in the unsearched 22% of the region, or it's not a planet. A primordial black hole fits that second possibility cleanly. It explains the gravitational signature. It explains why searches keep failing, and it doesn't require adjusting the mass or orbit estimates. You just swap the object type and everything else stays the same. The hypothesis also connects to a much bigger question in cosmology. Dark matter. The universe contains about 5 times more dark matter than ordinary matter. We know it's there because we can see its gravitational effects on galaxies, galaxy clusters, and the large-scale structure of the universe itself, but we don't know what it's made of. Decades of experiments have searched for dark matter particles, hypothetical new particles that don't interact with light or ordinary matter except through gravity. None of those experiments has found anything conclusive. The particle candidates are running out, and some researchers have started looking for alternatives. Primordial black holes are one of those alternatives. If the early universe produced a large population of small black holes, and if those black holes are still around today, they could account for some or all of the dark matter we observe. They would have mass, they would pull on galaxies, they would be invisible, and they would naturally explain why particle searches keep failing. Dark matter wouldn't be a new kind of particle, it would be an old kind of black hole. The idea has been around since the 1970s, proposed by Stephen Hawking and others as a way to solve the dark matter problem without invoking exotic physics. The problem is that most observational constraints have ruled out primordial black holes in certain mass ranges. Too many small black holes would have disrupted star formation in the early universe. Too many large black holes would show up in gravitational lensing surveys that have already been conducted. The mass range that remains plausible sits right around a few tens of Earth masses, exactly where Planet 9 sits. If Planet 9 is a primordial black hole, it would be the first direct detection of a dark matter candidate that isn't a particle. That discovery would be far more significant than finding another planet. A new planet is interesting. It changes the map of the solar system. It gives planetary scientists a new object to study. But it doesn't change the rules. A primordial black hole in the outer solar system changes the rules. It means the early universe left fossils scattered throughout the galaxy. It means dark matter might not be a particle at all. It means our own solar system, the place we've been studying for centuries, contains an object from the first microseconds of cosmic history. And it means that object has been hiding in plain sight for 4.5 billion years, shaping the orbits of distant worlds without anyone noticing until now. The possibility terrifies some researchers, not because black holes are inherently dangerous. A grapefruit-sized black hole at 400 astronomical units is not a threat to Earth. Its gravity drops off with distance just like any other mass. At our distance from the Sun, the pull from a 10 Earth mass object sitting in the outer Kuiper belt is negligible. You wouldn't feel it. The orbits of the planets wouldn't change. The only objects affected are those already in the outer solar system, the trans-Neptunian objects whose orbits are extreme and detached. The terror comes from the implications. If a primordial black hole is sitting in our solar system, how many others are out there? How many are drifting through the galaxy undetected? And if one happened to pass closer to the inner solar system, closer than a few hundred AU, what would it do to the planets? The answer depends on the trajectory. A black hole passing through the solar system on a hyperbolic orbit, not bound to the Sun but just swinging by, would perturb the orbits of planets slightly as it passed. The effect would be measurable but not catastrophic unless the black hole came extremely close, within a few AU. The odds of that happening are astronomically small. Space is big. The solar system is a tiny target. And primordial black holes, if they exist in large numbers, are spread out across the galaxy with vast distances between them. The chance of one passing close enough to Earth to matter in any human timescale is effectively zero. But effectively zero is not the same as impossible. And the fact that we wouldn't see it coming until it was already here, until its gravity started pulling on the planets in ways that didn't match our predictions, is what keeps the scenario lodged in the back of some astronomers' minds, not as a likely threat, as a reminder that the universe contains objects we can't see and processes we don't fully understand. The search for a primordial black hole in the outer solar system is only just beginning. Schultz and Unwin's proposal for a microlensing survey hasn't been funded yet, but the idea is gaining traction. Other researchers have suggested alternative detection methods, looking for the black hole's effect on the orbits of long-period comets, searching for faint X-ray emission if the black hole happens to be accreting a small amount of gas or dust from the interstellar medium, monitoring distant Kuiper belt objects for tiny accelerations that could indicate a close encounter with a compact, massive object. None of these methods is easy. All of them require years of data and instruments pushed to their limits. But they're possible. And the fact that the primordial black hole hypothesis makes specific testable predictions means it's not just speculation, it's science. The hypothesis also reframes the entire Planet 9 debate. For the last decade, the argument has been whether the clustering is real or an artifact of observational bias, whether the statistics hold up, whether a planet of the predicted mass and orbit could have formed in the outer solar system, or whether it had to have been captured from somewhere else. Those are important questions, but they all assume the unseen object is a planet. If it's a black hole, the formation question disappears. Primordial black holes don't form in solar systems. They formed in the early universe and have been drifting through space ever since. One of them could have been captured by the sun's gravity billions of years ago, just like a rogue planet could have been captured. The capture mechanism is the same. A passing object moving slowly enough relative to the sun that its trajectory bends into a bound orbit. Once captured, the object stays captured. It doesn't matter whether it's made of rock or space-time. Gravity doesn't care. And if the object is a primordial black hole, the searches that have been conducted so far were never going to find it. 78% of the predicted regions surveyed, 0 detections. That doesn't rule out Planet 9, it just means the planet is fainter or farther than expected. Or it means the surveys were looking for the wrong thing. A black hole doesn't show up in an optical or infrared image as a point of light. It shows up as nothing, a blank spot where a background star might flicker for a few hours before returning to normal. If the surveys weren't specifically designed to catch that kind of transient event, they would miss it entirely. And most of the surveys conducted so far were designed to find planets. Faint, slow-moving dots of reflected or emitted light, not invisible masses that only reveal themselves through the bending of space-time. The next generation of surveys will be different. The Vera Rubin Observatory, with its ability to scan the entire southern sky every few nights, will catch transient events by default. If a primordial black hole lenses a background star anywhere in Rubin's field of view, the event will show up in the data. The challenge will be distinguishing it from the thousands of other transient events Rubin will detect. Asteroids, variable stars, supernovae, gamma-ray bursts, all of them produce brightness changes that could be confused with microlensing. Sorting through the noise to find the one event that matches the signature of a compact mass moving at a few kilometers per second relative to the sun will require sophisticated algorithms and a lot of patience, but it's doable. And if the event is found, follow-up observations could confirm it by watching how the lensing signature evolves over time. A black hole on a bound solar orbit moves predictably. Track it for a few months and you can calculate its trajectory. Track it for a few years and you can pin down its mass and orbital parameters. That confirmation would answer the Planet 9 question once and for all. Not by finding a planet, by finding something that does everything a planet does without being one. The clustering would make sense, the high inclination orbits would make sense, the retrograde population would make sense, and the failure to detect Planet 9 in optical and infrared searches would make sense too. The surveys weren't failing because the planet was too faint. They were failing because they were looking for an object that emits or reflects light in a region of space occupied by an object that does neither. And standing at that realization, staring at the possibility that the outer solar system is being shaped by a relic of the Big Bang, the response isn't relief, it's unease. Because if a primordial black hole is hiding in the Kuiper belt, shaping orbits and bending spacetime without anyone noticing for billions of years, the obvious next question is what else is out there? How many other black holes are drifting through the galaxy? How many passed through the solar system in the distant past and left no trace because nothing was watching? How many are on trajectories that will bring them close in the future, close enough to perturb a planet? Close enough to scatter comets into the inner system, close enough to be detected only when their gravity starts pulling on things in ways we can't ignore. The universe has been running for nearly 14 billion years. It's had a long time to scatter objects into orbits we aren't tracking, and the fact that one of them might be sitting in our own cosmic backyard, invisible and patient, shaping the solar system with nothing but the weight of space-time itself, is a reminder that the map is never finished. There are always edges we haven't explored, always objects we haven't found, and sometimes those objects, when we finally notice them, turn out to be far stranger than anything we were looking for. Gravity does not compromise. It does not negotiate. It does not care about your predictions or your theories or the tidy model of the solar system you built in your head during middle school science class. Gravity pulls, it bends, it twists. And when you place a mass 10 times heavier than Earth on a tilted orbit at the far edge of the solar system and leave it there for billions of years, gravity does something far more subtle and far more terrifying than simply yanking things around. It sculpts, it organizes. It imposes order on chaos so slowly and so quietly that by the time anyone notices, the architecture of the entire outer solar system has been rewritten without anyone giving permission. That is what Planet 9, or whatever is hiding out there, has been doing. Not occasionally, not in brief dramatic bursts, constantly. Every second of every day for the entire history of the solar system, an invisible mass has been exerting a slow, steady torque on everything drifting through the Kuiper belt and beyond. The objects we call trans-Neptunian bodies are not moving randomly, they are dancing, and the choreographer is something no one has ever seen. The concept of gravitational sculpting is easy to misunderstand because gravity in everyday life feels simple. Drop a ball and it falls. Throw it sideways and it arcs. The trajectories are clean and predictable. But that simplicity only works when the timescales are short and the masses are small. Scale up to planetary masses and billion-year timescales, and gravity stops being a force that pulls things in straight lines. It becomes an architect. It builds structures. It carves rivers through orbital space the same way water carves canyons through rock. Slowly, patiently, inevitably. Start with the basic geometry. Planet 9, according to the models, orbits the Sun on an elliptical path tilted about 15 to 25 degrees relative to the plane where the 8 known planets orbit. Its semi-major axis, the long radius of the ellipse, sits somewhere between 400 and 800 astronomical units. Its perihelion, the closest point to the Sun, might be as near as 200 AU. Its aphelion, the farthest point, could reach 1200 AU or more. That orbit takes between 10,000 and 20,000 years to complete. One trip around the Sun. 10,000 years. For context, 10,000 years ago humans were just figuring out agriculture. Writing hadn't been invented yet. The pyramids were still 7,000 years in the future. Planet 9 has orbited the Sun only a few hundred times since the solar system formed, maybe 1,000 at most. It moves like a clock with a hand so slow you could watch it for a lifetime and never see it tick. But slow does not mean weak. The gravitational field of a 10 Earth mass object extends outward in all directions, dropping off with the square of the distance but never disappearing entirely. At 400 AU, Planet 9's gravity is faint. A Kuiper belt object passing at that distance would feel only a tiny tug, a barely perceptible nudge. But nudges accumulate. An object on an elliptical orbit swings out to the far reaches of the solar system, passes near Planet 9's orbital path, gets nudged slightly, swings back toward the Sun, completes the loop, and passes near Planet 9's path again. Another nudge, another slight change in velocity. Over thousands of orbits, those nudges add up to major changes in trajectory. The object's orbit precesses, rotating slowly around the Sun like the hands of a broken clock. Its inclination shifts, its perihelion distance drifts, and if the timing is just right, if the object keeps returning to the same region of space at roughly the same point in Planet 9's orbit, the nudges stop being random. They lock into a pattern, a resonance. Resonances are everywhere in the solar system. Jupiter's moons Io, Europa and Ganymede orbit in a 4:2:1 resonance. For every 4 times Io circles Jupiter, Europa circles twice and Ganymede circles once. The pattern is stable. It has lasted billions of years. The resonance protects the moons from chaotic interactions that would otherwise destabilize their orbits. The same principle applies to Planet 9 and the trans-Neptunian objects. If an object's orbital period is a simple fraction of Planet 9's period, the two bodies will encounter each other at the same relative positions over and over again. The planet's gravity pulls the object in the same direction every time. The orbit doesn't get randomized, it gets organized. Batygin and Brown's simulations showed this process playing out over millions of years. They started with a simulated population of Kuiper belt objects scattered randomly throughout the outer solar system. Then they added Planet 9, a 10-Earth mass body on a highly eccentric orbit tilted relative to the plane of the planets. They let the simulation run forward, calculating how each object's orbit evolved under the combined gravitational influence of the Sun, the 8 known planets, and the unseen 9th planet. The results were striking. Within a few tens of millions of years, the random distribution of orbits began to organize itself. Objects that started out with perihelia pointing in all different directions gradually clustered into a narrow range of angles, their orbital planes tilted and aligned. The ones that didn't align got scattered into different orbits or ejected from the solar system entirely. What remained was a population of trans-Neptunian objects whose orbits all pointed in roughly the same direction, away from Planet 9's perihelion, anti-aligned, shepherded into a configuration where they never came close to the planet even though their orbits crossed the same region of space. This is not a collision avoidance mechanism in the usual sense. The objects are not sentient, they are not steering. They are responding to gravity in the only way gravity allows. Over millions of years, the ones whose orbits brought them close to Planet 9 at the wrong time got flung out of the resonance. Their orbits changed. They either moved into a more stable configuration or got ejected entirely. The ones whose orbits kept them safely away from close encounters stayed in place. The resonance filtered the population. What we observe today, the clustering, is the stable remnant of that filtering process. The survivors, the objects whose orbits happened to fit the pattern Planet 9 imposed. The torque is subtle but relentless. Picture a spinning top. If you tap it gently on one side, the top wobbles. Tap it again in the same spot a few seconds later, and the wobble grows. Keep tapping at regular intervals, and eventually the top's axis of rotation shifts. It precesses. The same thing happens to orbits under sustained gravitational influence. Planet 9 exerts a torque on the orbital angular momentum of trans-Neptunian objects. Each close pass exchanges a tiny amount of momentum between the planet and the object. The object's orbit precesses. The long axis of the ellipse rotates. The plane of the orbit tilts, and because Planet 9 itself is on a tilted orbit, the torque doesn't push all objects into the same plane. It pushes them into a range of planes, all tilted in a coordinated way, all responding to the same underlying gravitational field. The simulations predict specific outcomes. Objects with semi-major axes, the long radius of their orbits, greater than about 250 AU and perihelia beyond 30 AU should show strong clustering in their arguments of perihelion. That is the angle that describes where the orbit reaches its closest point to the Sun. The clustering should sit roughly opposite Planet 9's own perihelion, around 180 degrees away. Objects with semi-major axes above 400 AU should also show clustering in their longitudes of ascending node, the angle that describes where the orbit crosses the plane of the solar system. and some fraction of the population should end up on orbits tilted almost perpendicular to the plane of the planets, looping up and over the Sun's poles in configurations that the standard model of solar system formation does not predict. All of those outcomes have been observed. The clustering is there, the high inclination objects are there. The retrograde orbits, objects circling the Sun in the opposite direction from everything else, are there. Every prediction the simulations make about how a distant massive planet would sculpt the outer solar system matches what telescopes have found. That does not prove the planet exists. Matching predictions is not the same as direct observation, but it means the hypothesis is working. The model is doing what models are supposed to do. It is making specific testable claims about the real world, and the real world keeps confirming them. The time scale matters. Gravitational sculpting is not a fast process. The resonances take millions of years to lock in. The precession happens on time scales of tens of millions of years. The orbital planes shift over hundreds of millions of years. These are not events you can watch in real time. They are geological in scale, slower than continental drift, slower than mountain building, but just as inevitable. And because the solar system is 4.5 billion years old, there has been plenty of time for Planet 9 to impose its will. If the planet formed early, either in place or captured within the first few 100 million years after the Sun ignited, it has had 4 billion years to organize the outer solar system. That is more than enough time for every unstable orbit to get cleared out and every stable configuration to settle into place. What we see today is not a snapshot of chaos. It is a snapshot of equilibrium. A system that has been running long enough to reach a steady state. Visualizing the gravitational field helps. Imagine a three-dimensional grid stretching outward from the Sun. At every point in that grid, the gravitational pull from the Sun and the planets combines to create a net force. Most of the time, the Sun dominates. Its gravity is so much stronger than anything else in the solar system that objects far from the planets mostly just follow simple elliptical paths around the Sun. But add Planet 9 and the grid changes. The field gets warped. In the region where Planet 9 orbits, the gravitational pull is no longer symmetric. It points slightly off-center, tilted by the planet's mass. Objects passing through that region feel the asymmetry. Their trajectories bend, not dramatically, not enough to send them careening into the Sun or out of the solar system in a single pass, just enough to shift their velocity by a fraction of a percent. That tiny shift changes the orbit. The next time the object comes around, it returns to a slightly different position. Another pass, another shift. Over thousands of orbits, the cumulative effect becomes enormous. The resonance works because the shifts are not random. If Planet 9 were moving on a circular orbit in the same plane as the other planets, its gravitational influence would average out. Objects passing on one side would get pulled one way. Objects passing on the other side would get pulled the opposite way. The net effect over many orbits would be small. But Planet 9 is on an eccentric orbit tilted relative to the plane. That breaks the symmetry. The planet spends most of its time at the far end of its orbit, where it moves slowly. Objects encountering the planet in that region feel a prolonged gravitational influence. The planet is not zipping past. It is hanging around, exerting a steady pull for a significant fraction of the object's orbital period. That sustained influence is what locks the resonance in place. The timing becomes predictable. The object returns to the same region at the same point in Planet 9's orbit. The pull is always in the same direction. The orbit precesses in a coordinated way. The clustering emerges naturally from the dynamics. There is another effect, the inclination pumping. Planet 9's gravity does not just shift where objects reach perihelion. It shifts the angle at which they orbit. Imagine a coin spinning flat on a table. That is an object orbiting in the plane of the solar system. Now tilt the table. The coin keeps spinning, but its orbit relative to the original reference frame is no longer flat. It is inclined. Planet 9, orbiting on a tilted path, exerts a torque that gradually tilts the orbits of smaller objects. Some get tilted a little, some get tilted a lot, and a few get tilted so much that their orbits flip entirely, looping over the sun's poles in near perpendicular paths. These high-inclination outliers are exactly the kind of objects that should not exist in a solar system that formed from a flat disk of gas and dust. Everything should be orbiting in roughly the same plane because everything came from the same spinning cloud, but they are not. The observations show a population of trans-Neptunian objects with inclinations above 60 degrees, some above 80 degrees, a few above 90, fully retrograde. Planet 9 predicts them, the simulations produce them, the standard model does not. The retrograde objects are particularly telling because flipping an orbit is hard. It requires a sustained torque applied over millions of years in just the right way to gradually rotate the orbital plane past 90 degrees. A single close encounter with a planet would not do it. Close encounters change orbits suddenly, violently. They scatter objects into new trajectories, but they do not flip them smoothly into retrograde configurations. That requires a long-term resonance with a massive distant body that keeps nudging the orbit in the same rotational direction until the plane flips. Planet 9, sitting on its tilted eccentric orbit, provides exactly that kind of sustained torque. The simulations show that a small fraction of trans-Neptunian objects, maybe a few percent, will end up retrograde after a few 100 million years of interaction with the planet. The fraction is small because the resonance that produces retrograde orbits is less stable than the resonances that produce prograde clustering. Most objects do not stay locked in long enough to complete the flip, but some do, and we have found them. The effect extends inward too. Planet 9 is far away, yes, but its gravitational influence does not stop at the Kuiper belt. It reaches all the way into the inner solar system. The pull is weaker there, much weaker, but over billions of years even a weak pull adds up. Batygin and collaborators ran simulations in 2021 that tracked how a distant massive planet would perturb the orbits of asteroids, centaurs and comets inside Neptune's orbit. The perturbations were tiny, a shift of a few degrees in inclination, a change of a few AU in semi-major axis, nothing you would notice over a human lifetime or even over recorded history. But the simulations showed that the statistical distribution of those orbits, the overall shape of the population, was subtly different in a solar system with Planet 9 than in one without it. And when the researchers compared the simulated distributions to the observed distributions, the version with Planet 9 matched better. Not perfectly. The inner solar system is complicated. Jupiter and Saturn dominate the dynamics. Planet 9's influence is a faint background signal buried under much stronger effects, but it is there, detectable, measurable. There is also the obliquity problem. The Sun's equator is tilted 6 degrees relative to the plane where the planets orbit. Nobody has fully explained that tilt. In a solar system that formed from a flat rotating disk, you would expect the Sun's spin axis and the orbital plane of the planets to be aligned. The Sun formed from the same disk. It should be spinning in the same direction as the planet's orbit, and it is, but it is also tilted 6 degrees off. That tilt has been known for decades. It has been measured precisely. But no mechanism in the standard model of solar system formation produces it. Turbulence in the protoplanetary disk could tilt things slightly, but not by 6 degrees and not in a way that would remain stable over billions of years. Something torqued the sun or the planets or both. Something with enough mass and enough leverage to shift the entire inner solar system slightly out of alignment. Planet 9 fits. The simulations show that a 5 to 10 Earth mass planet on a tilted orbit at 400 to 800 AU would exert a slow, steady torque on the inner planets over billions of years. The torque would cause the plane of the planets to precess, rotating slowly like a wobbling dinner plate, and the Sun, which is much more massive than the planets but also much less responsive to external torques, would lag behind. The result, after 4 billion years, would be a 6-degree offset between the Sun's spin axis and the orbital plane. Not 7 degrees, not 5, 6. The simulations match the observations with uncomfortable precision. That match does not prove Planet 9 exists, but it adds another entry to the list of puzzles the planet solves: the clustering, the high inclinations, the retrograde orbits, the smooth perihelion distribution, the inner solar system perturbations, the Sun's obliquity. Each one on its own could be a coincidence, a statistical fluke, an artifact of incomplete data. But taken together they form a pattern, a coherent set of effects that all point to the same cause. A massive distant object, exerting a sustained gravitational influence on every part of the solar system, from the innermost asteroids to the farthest detached Kuiper Belt objects. And the only way to produce that pattern, according to the simulations, is to have the object actually be there. The stability of the resonances is what makes the hypothesis testable. If Planet 9 is real, the clustering should not be temporary. It should be a permanent feature of the outer solar system maintained by an ongoing gravitational influence. New trans-Neptunian objects discovered in the future should continue to fit the pattern. Objects whose orbits are measured more precisely as better data comes in should continue to show clustering in the same angular ranges. And if the planet is eventually found, its mass and orbit should match the predictions closely enough that the simulations can be rerun with the real parameters and produce the same clustering. That is falsifiability. That is how science is supposed to work. You make a prediction, you test it. The universe either confirms the prediction or it doesn't. The alternative explanations have trouble with stability. If the clustering is the result of a passing star that disrupted the outer solar system billions of years ago, the perturbation would be temporary, the orbits would drift over time, the clustering would dissolve. Simulations of stellar flybys show that the effects fade within a few 100 million years as the perturbed objects spread out and their orbits randomize. But the clustering we observe today is sharp. The angles are tightly grouped. That suggests the organizing force is still active, still pulling, still sculpting. A one-time event in the distant past does not produce that kind of ongoing structure. The primordial disk hypothesis has the same problem. If a massive disk of material existed in the early solar system and exerted enough collective gravity to organize distant orbits, that disk would need to have persisted for hundreds of millions of years to lock the resonances in place. But disks dissipate. Gas gets blown away by the solar wind. Dust clumps into larger bodies or drifts inward. Within a few tens of millions of years, protoplanetary disks are gone. The material either forms planets or escapes. A disk massive enough to organize the outer Kuiper Belt would have left other traces. It would have affected the orbits of the giant planets. It would have altered the distribution of objects in the inner Kuiper Belt. We do not see those traces. The only structure we see is in the distant, detached population. The population that sits far enough out that Neptune could not have scattered it, and far enough in that a passing star would not have left it alone. The population that sits exactly where Planet 9's influence should dominate. The simulations also test what happens if you remove Planet 9. Run the same orbital integrations with the Sun and the 8 known planets, but no hidden ninth body. Let the trans-Neptunian objects evolve under that gravitational field for a few 100 million years. The result is chaos. The orbits randomize, the clustering dissolves, the high-inclination objects get scattered into more typical configurations or ejected entirely. The system does not settle into the structure we observe. It drifts into a configuration that looks nothing like the real solar system. Add Planet 9 back in and the structure re-emerges, the clustering reforms, the resonances lock, the high-inclination population stabilizes, the simulated solar system starts to look like the real one. That cause and effect relationship is what makes the hypothesis compelling. You are not just explaining one anomaly. You are explaining an entire interconnected web of anomalies that all respond to the same underlying cause. Remove the cause and the web falls apart. Restore the cause and the web rebuilds itself. That is not proof, but it is as close to proof as you can get without direct observation. The hypothesis is not just consistent with the data. It predicts the data. It tells you what you should see before you see it. And when you look, it is there, standing at this point in the argument, staring at the simulations and the observations and the growing pile of evidence that all points in the same direction. The response is not satisfaction, it is frustration, because the math works, the physics works, the predictions work, and the planet is still invisible. Somewhere out there, beyond the orbit of Neptune, beyond the Kuiper belt, beyond the scattered disk, a mass 10 times heavier than Earth is warping the solar system with nothing but gravity and time. It has been doing it for billions of years. It will keep doing it for billions more. And we cannot see it. We can only see what it does, the bent orbits, the clustered angles, the high inclinations, the retrograde paths. The fingerprints of a massive invisible hand reaching across hundreds of AU and gently, patiently sculpting the outer solar system into a shape that should not exist without it. The tug-of-war is not violent, it is not sudden, it is slow, methodical, and utterly relentless. And every trans-Neptunian object drifting through the dark is a piece of evidence that the war has been going on longer than humanity has existed and will continue long after we are gone. The question is no longer whether something is pulling. The question is whether we will find it before it finishes rewriting the map. The planet, if it exists, is hiding. Not casually, not the way a sock hides under a bed or your keys hide in a jacket pocket. It is hiding the way a needle hides in a haystack the size of Texas. Except the haystack is the southern sky, the needle is darker than charcoal, and it is moving so slowly that you could watch it for a month and mistake it for a distant galaxy that is not moving at all. This is not a search. This is an exercise in patience, precision, and the kind of stubborn optimism that keeps astronomers scanning the same patch of sky year after year, knowing full well that what they are looking for might not be there. For the last decade, teams around the world have been hunting Planet 9 using every tool in the astronomical arsenal. Wide-field surveys that scan huge sections of sky in single exposures, deep imaging campaigns that stare at the same spot for hours, trying to pull faint signals out of the noise, infrared telescopes that detect heat rather than reflected light, citizen science projects that recruit thousands of volunteers to comb through archival data, looking for anything that moved between images taken years or decades apart. And despite all of that effort, despite thousands of hours of telescope time and millions of images analyzed, the scoreboard reads the same. Planet 9, 0 direct detections, gravitational evidence mounting. It is the most frustrating kind of scientific problem. The one where the data keeps telling you something is there but refuses to show you what. The challenge starts with brightness, or the lack of it. A planet at 400 to 800 astronomical units from the Sun is receiving almost no sunlight. The intensity of sunlight drops with the square of the distance. At Earth's distance 1 AU, we get the full blast of the Sun's radiation. At Neptune's distance 30 AU, sunlight is about 900 times dimmer. At 400 AU, it is 160,000 times dimmer. And Planet 9, if it is out there, is not just sitting at 400 AU absorbing that faint sunlight. It has to reflect some of it back toward Earth. Rock and ice are not perfect mirrors. They reflect maybe 30 to 50% of the light that hits them, depending on the surface composition. The rest gets absorbed. So take the already dim sunlight reaching Planet 9, cut it in half for reflection losses, and then watch that reflected light travel 400 AU back to Earth, dimming again by the square of the distance. By the time the light arrives, Planet 9 would appear roughly 6 million times fainter than it would if it were sitting at Earth's distance. 6 million times. For comparison, Pluto, sitting at about 40 AU, is faint enough that you need a decent amateur telescope to see it at all. It sits right at the edge of naked eye visibility under perfect conditions, which means it is not visible under any realistic conditions. Planet 9 would be about 100 times farther than Pluto and correspondingly much, much dimmer. Estimates put its apparent magnitude somewhere around 22 to 24. Magnitude is an astronomer's way of measuring brightness. Lower numbers are brighter. The faintest stars you can see with your naked eye are about magnitude 6. Pluto is magnitude 14. The Hubble Space Telescope can detect objects as faint as magnitude 31 under ideal conditions. Planet 9 sits somewhere in the middle of that range. Detectable in principle, but only if you know exactly where to point the telescope, and only if you stare long enough to separate the signal from the noise. The problem is that you do not know where to point. The predicted orbit is enormous. At 400 to 800 AU, the planet could be anywhere in a swath of sky covering thousands of square degrees. For reference, the full moon covers about half a degree. The entire sky, from horizon to horizon in all directions, is about 41,000 square degrees. Planet 9 could be occupying any one of a few thousand of those degrees, and it is moving so slowly that you cannot just take a single image and spot it by eye. You need multiple images taken weeks or months apart. Then you need to compare them. Look for anything that shifted position between frames, and the shifting has to match the expected motion of a distant solar system object, not the motion of an asteroid which zips across the sky in hours or days, not the motion of a background galaxy which does not move at all on human timescales, the motion of a trans-Neptunian object which drifts a fraction of an arcsecond per hour. An arcsecond is 1/3600th of a degree. You are looking for something moving slower than the hour hand on a clock, dimmer than almost anything in the sky, buried in a field of millions of stars and galaxies that all look similar at first glance. Current search strategies break into a few categories. Wide field surveys scan large areas quickly, trading depth for coverage. These surveys take relatively short exposures, maybe a few minutes per field, and move on. They are optimized for finding brighter objects or catching transient events like supernovae. Deep imaging campaigns do the opposite. They stare at smaller regions for much longer, stacking multiple exposures to pull out faint signals. These surveys go deep but cover less sky. Then there are the infrared searches. Telescopes like WISE, the Wide Field Infrared Survey Explorer, and Spitzer, now retired, scan the sky in wavelengths where cold objects emit thermal radiation rather than reflecting sunlight. If Planet 9 is warm enough, and if its thermal emission is strong enough, Infrared surveys might pick it up, even if optical surveys miss it. WISE launched in 2009 and spent about a year scanning the entire sky in 4 infrared bands. Its job was to catalogue asteroids, brown dwarfs, distant galaxies, anything that glows in the mid-infrared. The mission was wildly successful. It found thousands of asteroids and hundreds of previously unknown brown dwarfs, small failed stars that never ignited fusion but still glow faintly from leftover heat. After its primary mission ended, WISE was brought out of hibernation for an extended mission called NEOWISE, focused on near-Earth objects. The data from both missions has been combed repeatedly for signs of Planet 9. Researchers have searched for faint infrared sources that moved between WISE's early observations and later follow-up scans. They have cross-referenced WISE data with older infrared surveys like IRIS from the 1980s to look for objects that shifted position over the decades. A few candidates have shown up. Faint sources that appear in multiple surveys and seem to have moved. But follow-up observations have either ruled them out as background objects or failed to confirm them as real. So far, WISE has not found Planet 9. But it has not ruled it out either. The surveys were not deep enough to detect an object at the faint end of the predicted brightness range, and they did not cover every part of the sky at the times when Planet 9 might have been brightest. Spitzer, which operated from 2003 until 2020, had a narrower field of view but could go deeper in some wavelengths. Researchers used Spitzer to search specific regions where Planet 9 might be lurking based on updated orbital predictions. Again, no detections. The absence of a detection in infrared does not rule the planet out. It just means the planet is either colder than expected, farther than expected, or sitting in a part of the sky that the infrared surveys did not adequately cover. Infrared telescopes have limited lifetimes. Their instruments need to be cooled to extremely low temperatures to function, and the coolant eventually runs out. Both WISE and Spitzer are no longer operating in their deepest infrared modes. Future infrared searches will need new missions or repurposed data from other surveys. Ground-based telescopes have been running their own campaigns. The Subaru telescope in Hawaii is one of the best tools for this kind of search. It has a large mirror, 8.2 meters across, and a wide field camera that can image large sections of sky in a single exposure. Subaru has been used extensively to search for distant trans-Neptunian objects, and some of the discoveries that strengthened the Planet 9 hypothesis came from Subaru observations. The telescope is optimized for faint object detection. Its location on Mauna Kea, above much of Earth's atmosphere, gives it a clearer view of the sky than most ground-based observatories. But even Subaru has limits. It cannot scan the entire predicted region in a reasonable amount of time. Each field takes time to expose, and the telescope has other science programs competing for time. Searching for Planet 9 is a marathon, not a sprint. The Keck Observatory, also in Hawaii, has contributed to the search as well. Keck has adaptive optics that correct for atmospheric distortion in real time, allowing it to achieve sharper images than most ground-based telescopes. That precision helps when you are trying to separate a faint moving object from a dense background of stars. But Keck's field of view is smaller than Subaru's, which makes it better suited for follow-up observations than large-scale surveys. If a candidate is identified in a wider survey, Keck can take a closer look and confirm whether it is real. Then there is the citizen science angle. NASA launched a project called Backyard World's Planet 9 that invites volunteers to search through archival data from WISE, looking for moving objects that automated algorithms might have missed. The project works by showing users pairs of images taken years apart and asking them to identify anything that shifted position. Humans are surprisingly good at this kind of pattern recognition. Our brains are wired to spot things that do not belong. Automated algorithms can be fooled by noise, cosmic rays, or artifacts in the images. A trained human eye can tell the difference. Thousands of people have participated in backyard worlds, and the project has led to the discovery of dozens of brown dwarfs and other objects. But so far, no Planet 9. The search continues. By some estimates, prior efforts have now ruled out about 78% of the possible sky region where Planet 9 could be hiding. That number comes from Brown and Batagin's team, who have been updating their predictions as new data comes in and as search campaigns eliminate chunks of the parameter space. 78% sounds like a lot. It is a lot. But it also means 22% remains unsearched. And if Planet 9 is sitting in that remaining 22%, or if it is fainter than the surveys could detect, then the searches so far have been looking in the right neighborhood but missing the house. The next phase of the hunt hinges on a single telescope, the Vera the 100th Rubin Observatory, sometimes called LSST, the Legacy Survey of Space and Time. Rubin is not just another telescope. It is a purpose-built machine designed to do one thing better than any other instrument ever constructed: scan the sky, fast, deep and wide, over and over again, every few nights for 10 years. Rubin sits on Cerro Pachon in the Chilean Andes, a site chosen for its clear skies and minimal light pollution. The telescope has an 8.4-meter mirror comparable to Subaru and Keck, but its real advantage is the camera, the largest camera ever built for astronomy, 3.2 billion pixels. For context, a high-end consumer camera has about 50 million pixels. Rubin's camera has 3,200 million. It can image an area of sky about 40 times the size of the full moon in a single exposure. That combination of size and resolution means Rubin can go deep and wide simultaneously. Most telescopes have to choose, Rubin does not. The survey strategy is what makes Rubin uniquely suited for finding Planet 9. Starting in the mid-2020s, the telescope will scan the entire southern sky every 4 nights, not selectively, not targeting specific regions, the entire visible southern hemisphere. Every patch of sky will be imaged multiple times per week, and because the exposures are stacked and compared over time, anything that moves will stand out. Asteroids, comets, trans-Neptunian objects, anything with a measurable proper motion relative to the background stars. The system is automated. Rubin will generate about 20 terabytes of data every single night. That is 20,000 gigabytes per night. Over the course of the 10-year survey, the total data volume will be measured in petabytes. Automated pipelines will process the images, identify moving objects, and flag candidates for follow-up. Humans will never look at most of the raw data. The sheer volume makes manual inspection impossible. But the algorithms are good. They have been tested. And they are designed specifically to catch the kind of slow, faint motion that Planet 9 would produce. If Planet 9 is anywhere in the southern sky, and if it is brighter than about magnitude 24, Rubin will find it. Not might find it, will find it. Within a year or two of starting operations, according to some estimates. The telescope's repeated scans mean that even if the planet is near the edge of detectability, stacking multiple exposures will pull the signal out of the noise, and because Rubin images the same regions over and over, the motion will be unmistakable. A faint dot that appears in the same spot across multiple nights, shifting slightly between frames, moving at the rate expected for a distant solar system object. That is Planet 9, or it is a very distant asteroid, or it is a background galaxy with unusual properties that make it look like it is moving when it is not. Follow-up observations will settle the question, but the initial detection will come from Rubin. The timeline has slipped a few times. NASA originally expected Rubin to begin operations in 2025. Reports from 2024 and early 2025 suggested first light and full operations were imminent or scheduled for the following year. These delays are normal for a project of this scale. Building the largest astronomical camera in history and integrating it with a new telescope on a remote mountaintop does not happen on a fixed schedule. But the delays are frustrating for Planet 9 hunters because every year Rubin is not operational is another year the planet stays hidden. Batygin has said publicly that Rubin represents the best chance of settling the Planet 9 question within the next decade. Either the telescope finds the planet or it rules out the regions where the planet should be bright enough to detect, which would force a recalibration of the hypothesis. There is also a secondary outcome that matters just as much. Even if Rubin does not find Planet 9, it will find thousands of new trans-Neptunian objects. Objects that can be added to the orbital catalogue and tested against the clustering predictions. If the new objects continue to fit the pattern, the statistical case for Planet 9 strengthens even without a direct detection. If the new objects break the pattern, if they are scattered randomly across all orbital angles and inclinations, then the clustering we see today gets reinterpreted as a statistical artifact. A fluke that looked significant with a small sample but dissolved once the sample size grew. That outcome would not kill the Planet 9 hypothesis outright, but it would weaken it badly, and it would force researchers to look for alternative explanations. Rubin will answer that question too. One way or another, the survey will settle whether the orbital clustering is real or an artifact of biased observations. Batygin has described Rubin as a next-generation telescope that will survey the entire available sky every few nights. That phrase, entire available sky, is important. Rubin is in the southern hemisphere. It cannot see the northernmost parts of the sky. If Planet 9 happens to be in the far northern sky, Rubin will miss it. But the predicted orbit, tilted and elongated, spends most of its time in regions visible from both hemispheres, and the southern sky has been less thoroughly searched than the northern sky by previous surveys. If Planet 9 is hiding, the southern sky is where it is most likely to be. Rubin will search that region more thoroughly than any prior instrument. If the planet is there, it will show up. The data processing challenge is enormous. 20 terabytes per night is manageable for modern computing infrastructure, but only if the pipelines are efficient. The images need to be calibrated, stacked, compared, and analyzed in near real time. Moving object detection algorithms need to run continuously, flagging anything that shifts between frames. False positives, objects that look like they are moving but are not, need to be filtered out. And the sheer number of real moving objects, asteroids, Kuiper belt objects, comets, will overwhelm any system that is not designed to handle the volume. Rubin's pipelines have been tested on simulated data and smaller precursor surveys. The team is confident they can handle the load. But the real test will come when the telescope starts producing data at full scale. A single missed detection, a faint object that gets flagged as noise and discarded by the pipeline, could be Planet 9 slipping through the cracks. The algorithms need to be sensitive enough to catch everything, and robust enough not to drown the researchers in false positives. Another factor is timing. Planet 9, on its long elliptical orbit, is not equally bright at all times. If the planet is near aphelion, the farthest point from the Sun, it will be at its faintest. If it is near perihelion, the closest point, it will be brightest. But perihelion for Planet 9 is still a couple hundred AU. Even at its brightest, the planet will be extraordinarily dim. The question is whether Rubin will start its survey at a time when Planet 9 happens to be in a favorable position. If the planet is currently on the far side of its orbit, moving slowly through the faintest part of its brightness range, Rubin might detect it, but only barely. If the planet is closer in, or if it crosses into Rubin's field of view during a period when its motion is more pronounced, the detection will be cleaner. Timing matters, and nobody knows where on its orbit Planet 9 is right now. That uncertainty is baked into the search. The Subaru telescope, for all its contributions, cannot match Rubin's scale. NASA has said that Subaru is one of the best tools for picking out dim, extremely distant objects lost in huge swaths of sky. That is true. Subaru has found more distant trans-Neptunian objects than almost any other ground-based telescope, but Rubin will surpass it simply by covering more sky more often. Subaru can go deep in targeted regions. Rubin will go deep across the entire southern hemisphere repeatedly. For 10 years. That persistence is what makes the difference. A single image might miss Planet 9 because the planet is too faint, or because it is lost in the noise, but 10 images of the same region, stacked together, will pull the signal out. Rubin is designed for exactly that kind of iterative detection. One of the stranger aspects of the search is that researchers have to account for millions of background stars. At magnitude 22, Planet 9 would be dimmer than most stars visible in a deep image. The background is not empty, it is crowded. Every patch of sky contains thousands of stars, tens of thousands if you are looking toward the Milky Way. Planet 9 will look like just another faint star unless you catch it moving. That is why repeated imaging is critical. A star stays in the same place between exposures. A planet does not. The motion is the signature. But extracting that motion from a field of millions of static sources requires careful calibration and precise astrometry, the measurement of positions on the sky. Any error in how the images are aligned or how the positions are measured can introduce false motion or hide real motion. Rubin's pipelines are designed to handle this, but the margin for error is thin. There is also the question of what happens if Rubin finds something, not Planet 9 specifically, just something. A faint moving object at the right distance moving at the right speed. The first detection will not be definitive, it will be a candidate. Follow-up observations will be required to confirm the orbit, measure the brightness in multiple wavelengths, and rule out alternative explanations. Is it a planet? A large Kuiper Belt object? A distant asteroid? A background galaxy with unusual properties? The only way to know is to keep watching, track the object for months or years. Measure how its position changes over time, fit the observations to an orbit, and see if that orbit matches the predictions for Planet 9. If it does, if the mass and trajectory line up, then the hypothesis is confirmed. If it does not, then the search continues. Astronomy quoted researchers saying Rubin could find Planet 9 within a year or two if it exists and lies within expected bounds. That if carries weight. The planet has to exist. It has to be within the brightness range Rubin can detect. It has to be in the southern sky during the survey window, and it has to move in a way that the detection algorithms can catch. Any one of those conditions failing means the search drags on. But if all the conditions are met, the timeline is short. A year or two, maybe less. Starting from whenever Rubin begins full operations, which at this point is imminent. The anticipation in the planetary science community is palpable. This is the telescope that will settle the question, one way or another. Either Planet 9 shows up in Rubin's data, or the hypothesis has to be reconsidered. There is no middle ground. The search has been running for a decade. The gravitational evidence keeps piling up, the simulations keep working, and the technology to find the planet, if it is out there, is finally ready. Rubin is not perfect, no telescope is, but it is the best tool humanity has ever built for this specific job. Scanning the sky, finding faint moving things, doing it over and over until the thing that has been hiding finally runs out of places to hide. And that brings the story to a knife edge. The search is about to get an answer, not in some distant future, not in a generation. In the next few years, Rubin will either find Planet 9 or constrain the hypothesis so tightly that the remaining possibilities shrink to a handful of scenarios. If the planet is real, we will see it soon. If it is not, the clustering will need a new explanation, and that explanation will need to be at least as compelling as the one Planet 9 provides. Either outcome reshapes what we know, and standing on the edge of that discovery or that failure, the scientists hunting Planet 9 are not celebrating, they are not confident, they are terrified. Because finding a 10 Earth mass world hiding at the edge of the solar system is not the end of the story. It is the beginning of a much stranger one. And the implications of that discovery, the questions it raises and the assumptions it shatters, are what make Planet 9 not just interesting, but deeply, uncomfortably unsettling. The technology is ready, the telescope is built, the data is coming, and nobody knows what it will say. The technology is ready, the telescope is built, the data is coming, and standing on the edge of that discovery, the scientists hunting Planet 9 are not excited in the way you might expect. They are not giddy, they are not popping champagne, they are terrified. Not because finding a hidden planet is dangerous in the Hollywood sense. A 10 Earth mass world sitting at 400 astronomical units is not going to swoop in and collide with Earth. It is not going to destabilize the orbits of the inner planets. It is not going to shower us with comets or drag us into some gravitational death spiral. The planet, if it exists, has been sitting exactly where it is for 4.5 billion years. It will stay there for another 4.5 billion. The danger is not physical. The danger is conceptual. The danger is what the discovery would do to every assumption we have built about how the solar system formed, what it contains, and how much of it we actually understand. And if Planet 9 is not a planet at all, if it turns out to be something stranger, the implications get worse, much worse. Start with the simple scenario, the one where Rubin points its mirror at the southern sky, scans the predicted region, stacks a few dozen images, and there it is, a faint dot, magnitude 23. Moving at exactly the rate a distant solar system object should move. Follow-up observations confirm the trajectory, more images pin down the orbit. The math matches Batygin and Brown's predictions. Semi-major axis 450 astronomical units, eccentricity 0.3, inclination 20 degrees, mass 8 Earth masses, give or take. It is real. It has been there the whole time. Planet 9 is confirmed. That announcement would be one of the biggest stories in the history of astronomy, bigger than the discovery of Pluto, bigger than the discovery of Neptune. Because Pluto turned out to be small and Neptune was predicted by irregularities that turned out to be measurement errors, Planet 9 is neither. It is massive. It has reshaped the outer solar system. And it was found not by accident, but by following the evidence with the kind of precision that makes the scientific method look like it actually works. The discovery would validate a decade of research, confirm the gravitational models, and add a new major body to the inventory of the solar system. For a brief moment, the announcement would feel like a triumph. Then the questions start. Where did it come from? How did it get there? Why is it on such a weird orbit? And why did it take us this long to find it? Those questions do not have comfortable answers. The standard model of solar system formation says that planets form in a disk of gas and dust orbiting a young star. The disk is flat, Everything orbits in roughly the same plane. Planets grow by sweeping up material in their orbital paths. Small objects clump into larger ones. Larger ones grow into planetesimals. Planetesimals collide and merge into protoplanets. Protoplanets clear their orbits and become planets. The process takes a few tens of millions of years. By the time the disk dissipates, the planets are in place. They stay there, stable, orderly, done. Planet 9 does not fit that story. At 400 to 800 AU, it is too far from the Sun to have formed in place. The protoplanetary disk was not dense enough at that distance to build a planet. The material was too spread out. The timescale was too long. If you try to form a planet that far out using the standard accretion model, you run out of time before the disk evaporates. The gas gets blown away by the solar wind. The dust drifts inward or gets ejected. You do not get a planet. You get a scattered population of small, icy bodies. The Kuiper belt, not a 10 Earth mass world sitting in a stable orbit tilted relative to the plane of the other planets. So if Planet 9 did not form where it is, it had to come from somewhere else. The two main options are that it formed closer to the Sun and got scattered outward, or it formed around a different star entirely and got captured when that star passed close to the Sun billions of years ago. Both scenarios are possible. Neither is easy. Scattering a planet outward requires a gravitational kick from another massive object. Jupiter and Saturn could do it. Early in the solar system's history, the giant planets migrated. Their orbits shifted as they interacted with the disk and with each other. Some models suggest that the solar system originally had 5 giant planets, not 4. The 5th one got ejected entirely, flung out of the solar system by a close encounter with Jupiter. If that happened, it is plausible that another planet, smaller but still massive, got kicked into a distant eccentric orbit rather than ejected. That planet would be Planet 9. The problem is that most simulations of giant planet migration do not produce that outcome. The scattered planet usually either gets ejected entirely or crashes into one of the other giants. Getting it into a stable orbit at 400 AU with the right eccentricity and inclination is hard. Not impossible, but hard enough that you need very specific initial conditions. Fine-tuning. The kind of setup that makes theorists uncomfortable because it suggests the solar system is not typical, it is special. And special in science often means we are missing something. The capture scenario is even harder to swallow. If Planet 9 formed around another star and got captured when that star passed close to the Sun, the timing has to be perfect. The encounter has to happen early, within the first few 100 million years after the Sun formed, while both stars are still embedded in the same star-forming region. The passing star has to come close enough that its gravity can strip a planet from its own system and hand it off to the Sun, but not so close that it destabilizes the inner solar system or ejects the other planets. The captured planet then has to settle into an orbit that happens to match the configuration we observe today: tilted, eccentric, stable for billions of years. Run the simulations and the odds are not good. Captures happen, but capturing a planet into the exact orbit that Planet 9 is supposed to occupy, with the exact mass and inclination, is statistically unlikely. Possible, yes. Likely, no. Both explanations require invoking processes that are not part of the standard narrative. Either the solar system had a violent early history that scattered planets into configurations we do not fully understand, or the solar system captured a rogue planet from interstellar space in an encounter we have no direct evidence for. Either way, finding Planet 9 forces a rewrite, not a footnote, a rewrite. Textbooks will need new chapters, formation models will need new parameters, And every assumption about how typical the solar system is, how representative it is of planetary systems in general, gets called into question. Because if our solar system contains a hidden massive planet that took us this long to find, what else are we missing? How many other planetary systems have unseen objects lurking in their outer reaches? And how do you build a theory of planet formation that accounts for objects that do not show up in the data until you have been looking for a decade? Mike Brown, one of the scientists who proposed Planet 9, has been quoted saying that if the planet is confirmed, it would be the most planety of the planets in the whole solar system. That phrase sounds like a joke. It is not. What he means is that Planet 9, unlike the other planets, would be gravitationally dominant in its region. It would have cleared its orbit. It would be massive enough that everything else in its neighborhood responds to its gravity rather than the other way around. The definition of a planet, the one that got Pluto demoted, requires that a body has cleared the neighborhood around its orbit. Planet 9 does that. It is the shepherd. Everything else in the outer Kuiper belt is the flock. By the formal definition, Planet 9 is more of a planet than Pluto ever was. Brown also said that there have only been 2 true planets discovered since ancient times, and this would be a third. Uranus in 1781, Neptune in 1846, Planet 9 in 2020-something. Those discoveries are generational. They happen once in a lifetime if you are lucky, and they redefine what the solar system is. Uranus doubled the known size of the solar system. Neptune proved that math could predict the existence of unseen worlds. Planet 9, if confirmed, would prove that the solar system is bigger, stranger, and less thoroughly mapped than anyone alive today assumed. That realization is not comforting, it is humbling. And humbling is not an emotion scientists enjoy. Then there is the darker scenario, the one where Rubin scans the predicted region, finds nothing, and the searches continue for another few years with the same result. No planet, no thermal emission, no reflected light. The clustering remains. The high inclination objects remain. The retrograde orbits remain. The gravitational evidence keeps stacking up. But the thing causing it refuses to show itself. At that point, the hypothesis has to pivot. If it is not a planet, what is it? The answer that keeps surfacing, the one that sounds absurd until you look at the physics and realize it is not obviously wrong, is a primordial black hole. A black hole with the mass of 10 Earths would have an event horizon the size of a grapefruit. It would not glow. It would not reflect light. It would not emit heat in any detectable amount. The only way to know it is by watching what it does to everything around it. The orbits, the clustering, the slow, patient sculpting of the outer solar system over billions of years. A primordial black hole sitting where Planet 9 is supposed to be would produce exactly the same gravitational signature as a planet. Indistinguishable. The math does not care whether the mass comes from rock and gas or from a singularity wrapped in an event horizon. Mass is mass. Gravity is gravity. And if the searches keep failing, if Rubin and every other telescope pointed at the outer solar system comes up empty, the primordial black hole hypothesis stops being speculative and starts being the best explanation left on the table. That possibility terrifies scientists for reasons that have nothing to do with black holes being dangerous. A grapefruit-sized black hole at 400 AU is not a threat to Earth. Its gravity at our distance is negligible. You would not feel it. The planets would not feel it. The only objects affected are the ones already in the outer Kuiper belt, and they have been affected for billions of years without incident. The terror comes from what the discovery would mean. If Planet 9 is a primordial black hole, it is not just a new object in the solar system, it is a relic of the Big Bang, an object that formed in the first microseconds of cosmic history, drifted through space for 13 billion years, and got captured by the sun's gravity at some point in the distant past. It has been sitting in the outer solar system ever since, invisible, patient, shaping orbits without anyone noticing until now. Primordial black holes are hypothetical. Nobody has ever confirmed one exists. They are predicted by some models of the early universe, the ones that allow for density fluctuations to collapse into black holes before the expanding cosmos smooths them out. If those models are right, primordial black holes could be scattered throughout the galaxy, maybe throughout the universe. They would be invisible. They would not interact with light. They would only reveal themselves through gravity. And if one of them is sitting in our solar system, it means they are not just hypothetical. They are real, and they are everywhere. That realization connects Planet 9 to one of the biggest unsolved problems in cosmology: dark matter. The universe contains 5 times more dark matter than ordinary matter. We know it is there because we can see its gravitational effects on galaxies and galaxy clusters, but we do not know what it is made of. Decades of experiments have searched for dark matter particles, hypothetical new particles that do not interact with light or ordinary matter except through gravity. None of those experiments has found anything conclusive. The particle candidates are running out, and some researchers have started looking for alternatives. Primordial black holes are one of those alternatives. If the early universe produced a large population of small black holes, and if those black holes are still around today, they could account for some or all of the dark matter we observe. They would have mass, they would pull on galaxies, they would be invisible, and they would naturally explain why particle searches keep failing. Dark matter would not be a new kind of particle, it would be an old kind of black hole. The idea has been around since the 1970s, proposed by Stephen Hawking and others as a way to solve the dark matter problem without invoking exotic physics. Most observational constraints have ruled out primordial black holes in certain mass ranges. Too many small ones would disrupt star formation, too many large ones would show up in gravitational lensing surveys. But the mass range that remains plausible sits right around a few to a few tens of Earth masses, exactly where Planet 9 sits. If Planet 9 is a primordial black hole, it would be the first direct detection of a dark matter candidate that is not a particle. That discovery would be far more significant than finding another planet. A new planet is interesting. It changes the map of the solar system. It gives planetary scientists a new object to study, but it does not change the rules. A primordial black hole in the outer solar system changes the rules. It means the early universe left fossils scattered throughout the galaxy. It means dark matter might not be a particle at all. It means our own solar system, the place we have been studying for centuries, contains an object from the first microseconds of cosmic history. And it means that object has been hiding in plain sight for 4.5 billion years, shaping the orbits of distant worlds without anyone noticing until now. The implications ripple outward. If one primordial black hole is sitting in our solar system, how many others are out there? How many are drifting through the galaxy undetected? The Milky Way contains hundreds of billions of stars. If even a small fraction of them have captured primordial black holes into their outer systems, the galaxy is full of invisible massive objects that we have no way of tracking. And if primordial black holes make up a significant fraction of dark matter, the number could be in the trillions, scattered across the universe, invisible, waiting. Most of them would never come close to Earth. Space is big. The distances between stars are vast. The odds of a primordial black hole passing through the inner solar system, close enough to perturb the planets, are astronomically small. But astronomically small is not zero, and the fact that we would not see it coming, that the first sign of a close pass would be unexplained perturbations in planetary orbits, is what keeps the scenario lodged in the back of some astronomers' minds, not as a likely threat. as a reminder that the universe contains objects we cannot see and processes we do not fully understand. There is also the question of what a close encounter would look like. A primordial black hole passing within a few AU of Earth would not suck the planet in like a vacuum cleaner. Black holes do not work that way. They pull, just like any other mass. If the black hole is moving fast, on a hyperbolic trajectory through the solar system, it would pass by and leave. The gravitational tug would perturb Earth's orbit slightly. The effect would be measurable but not catastrophic. The planet would not spiral into the black hole. It would not get torn apart. It would just get nudged. A few kilometers per second change in velocity, enough to shift the orbit slightly, enough to alter the climate over thousands of years as the distance from the sun changed. Not enough to end civilization, not in the dramatic sense, but enough to matter. If the black hole is moving slowly, or if it gets captured into a bound orbit around the sun, the long-term effects get worse. A massive object orbiting inside the solar system would perturb the orbits of all the planets over millions of years. The inner solar system is dynamically stable now. The planets have settled into orbits that avoid close encounters. Add a new massive object, and that stability breaks. The orbits precess, the resonances shift, and over millions of years the configuration changes. Some planets get their orbits stretched, some get their inclinations tilted. In the worst case, a planet gets ejected entirely or crashes into another planet. The timescale is long, millions of years. Long enough that no human would live to see it, but short enough that the solar system as we know it, the one with 8 stable planets orbiting in predictable paths, would stop existing. That scenario is not likely. The odds of a primordial black hole getting captured into the inner solar system are vanishingly small. But the fact that it is possible, that the physics allows it, is unsettling. Because if primordial black holes are real, and if they are scattered throughout the galaxy, then every planetary system is playing a cosmic lottery. Most of them will never have a close encounter, but some will. And when they do, the planets in those systems get scrambled. The stable architectures get disrupted. The nice orderly orbits get replaced by chaos. And the civilizations that might have evolved on those planets, the ones that assumed their solar system was safe and predictable, find out the hard way that the universe does not care about their assumptions. The philosophical implications are harder to articulate, but just as significant. Humanity has spent the last few centuries building a model of the solar system based on observation, measurement, and prediction. We mapped the planets. We calculated their orbits. We sent probes to visit them. We assumed that what we could see was most of what mattered. The discovery of Planet 9, or a primordial black hole in its place, shatters that assumption. It means the solar system contains major objects we missed, not small asteroids or distant comets, major objects, massive enough to reshape entire populations of smaller bodies, massive enough to affect the dynamics of the system as a whole. And we missed them because they are too far, too faint, or too strange to show up in the searches we have been running for decades. That realization forces a recalibration of how much we actually know. Not just about the solar system, about the universe. Every map we have drawn, every model we have built, is based on the data we can collect. If major objects are hiding just outside the edge of our detection horizon, waiting to be found, then every map is incomplete, every model is provisional, and the confidence we have in our understanding of the cosmos is built on a foundation that might have gaps we have not noticed yet. That is not a comfortable position. It is the position of someone who thought they had finished exploring their house and then found a locked door they had never seen before. You do not know what is behind the door. You do not know how long it has been there. And you do not know what finding out will do to your sense of how the house is laid out. The scientists hunting Planet 9 are not afraid of the planet itself. They are afraid of what it represents. A challenge to the assumption that the solar system is fully mapped. A challenge to the models of planet formation that have guided the field for decades. A challenge to the idea that dark matter is a particle rather than a population of invisible black holes. And a challenge to the comforting fiction that the universe, for all its scale and strangeness, is at least predictable in the regions we have studied most carefully. Finding Planet 9, especially if it turns out to be a primordial black hole, means admitting that the solar system is bigger, stranger, and less understood than we thought. It means admitting that major discoveries are still waiting in our own cosmic backyard. And it means admitting that the edges of the map, the places we have not looked carefully, might contain things that rewrite the rules. The Rubin Observatory will settle this, one way or another. Within a few years, the telescope will either find Planet 9, rule out the regions where it should be detectable, or find something else entirely. Each outcome is uncomfortable in its own way. Finding a planet means rewriting solar system formation. Not finding a planet means the clustering needs a new explanation, and the alternatives are not less strange. Finding a primordial black hole means confronting the possibility that the universe left relics in our solar system that have been shaping it for billions of years without anyone noticing. There is no safe answer. Every possibility reshapes what we thought we knew. And standing at the edge of that discovery, watching the technology come online and the data pipelines prepare to process 20 terabytes per night, the scientists involved are not celebrating, they are bracing, because the history of astronomy is full of moments when a new observation forced a paradigm shift. Galileo saw moons orbiting Jupiter and proved that not everything orbits Earth. Hubble saw galaxies receding and proved the universe is expanding. The discovery of Neptune proved that math could find planets before telescopes did. Each of those discoveries was uncomfortable at first. Each one forced scientists to let go of assumptions they thought were solid, and each one, in hindsight, was the beginning of a deeper understanding. Planet 9, if it exists, will be another one of those moments. The kind that gets written into textbooks and remembered for generations. The kind that redefines what the solar system is and how much of it remains unexplored. And whether it is a planet, a black hole, or something no one has thought of yet, the discovery will carry the same message. The universe is not finished surprising us. The maps are not complete. And the assumption that we have found everything worth finding in our own neighborhood is wrong. There are still doors we have not opened, still regions we have not searched, still objects hiding in the dark, waiting for someone to point a telescope in the right direction at the right time and finally see what has been there all along. The fear is not that Planet 9 is dangerous. The fear is that it is real. And if it is real, then everything we thought we understood about the solar system, about planet formation, about dark matter, and about how thoroughly we have explored the cosmic space we call home, is going to need a revision. A big one. The kind that does not fit in the margins of a textbook. The kind that requires starting over. And the realization that we might be about to start over, that the data is coming and the answer is close, is what keeps the scientists awake. Not excitement, not pride, unease, because discovery is supposed to feel like triumph, but sometimes it feels like opening a door you thought was locked and finding a staircase leading down into darkness. You do not know how deep it goes. You do not know what you will find at the bottom, and you do not know if you are ready for the answer. But the staircase is there. And the only thing worse than going down would be pretending you never saw it. So here we are, Standing at the edge of a question that has been tightening its grip on planetary science for nearly a decade, something massive is pulling on the outer solar system. The math says so, the orbits say so, the simulations say so, and every new trans-Neptunian object discovered in the last few years has either strengthened the pattern or at minimum refused to contradict it. The clustering is real. The high inclination objects are real. The retrograde orbits are real. What remains unreal, at least for now, is the thing causing all of it. Planet 9, if it exists, is not just another object to add to the inventory. It is a mirror, a reflection of how much we assumed we had finished mapping and how wrong that assumption turned out to be. For centuries, humanity has looked outward and believed that the visible universe was most of what mattered. We found the planets. We calculated their orbits. We sent probes to visit them. We built models that worked, and then the data whispered that something was missing. Not a small thing, not an asteroid or a comet. A world, 10 times the mass of Earth, hiding in plain sight for 4.5 billion years, shaping the solar system with nothing but gravity and time while we looked the other way. The Vera Rubin Observatory will answer the question. Not someday, soon. Within a few years, the telescope will either find the planet, rule out the regions where it should be bright enough to detect, or find something stranger, a primordial black hole, a relic of the Big Bang, an invisible mass that does not belong to any category we have names for. Every outcome is uncomfortable. Every outcome forces a rewrite, and that discomfort is not a bug, it is the point, because the edge of the map has always been where the most important discoveries wait, not the places we have explored 100 times, the places we have been too confident to look. And whether Planet 9 is a planet, a black hole, or something else entirely, its discovery will carry the same message. The solar system is not finished. The maps are not complete.